So, good day to everyone. Welcome to CE014 Principles of Steel Design. So, before I start the discussion for today, may I just recap what we have studied from our last meeting. So, previously, we have learned about compression members. So, we have discussed Module 3 all about compression members. So we have familiarized ourselves with compression members. So we have familiarized ourselves with the different things where we can find compression members. We also discuss the basis of the different code provisions related to compression members, which is the Euler buckling theory, as well as the inelastic buckling. And then we also discuss about the local buckling of column sections. And then we we familiarize ourselves with the different code provisions for the analysis and design of compression members, as well as on how to compute for the effective length factors for frame columns. And lastly, we have discussed the different procedures for the analysis and design of columns or compression members in general. So for today, we will be discussing about Module 4, which will talk about flexural members. So we are now finished with discussing tension members, compression members. So now we will be moving on to the next member that we will be discussing, which are the flexural members. So we will talk about beams because most of the time flexural members are most of the time, beams are the most common lectural member that we use in civil engineering. Therefore, it's worthy to be familiar with the definition of beams, as well as on where will we most probably be encountering beams. And then let us have an introduction to the plastic analysis of beams, because this is the concept that is used for the derivation of the different code provisions related to beams or flexural members in general. And then let's talk about also about lateral torsional buckling and the local buckling of beam section. So these are the different limit states that we usually check whenever we design flexural members. And then let us just also have a uh, short discussion about the shear on beams and the different serviceability requirements for beams. And then, just like the usual, we will be familiarizing ourselves with the different code provisions related to the analysis and design of beams, as well as the different steps or procedures for analysis and design of beams. And then lastly, let us just have a quick discussion about the concentrated loads and holes on beams. So these are the topics that will be discussed for this module. So without further ado, let's start our discussion. So let's start with discussing about beams, because just like what I've said a while ago, beams are usually the most common flexural member that we will be encountering in civil engineering. So when we say beams, beams are structural members that mainly support transverse loadings, usually due to gravity loads such as dead loads and live loads. So that this is the main difference between a beam or a flexural member compared to the other member that we have discussed. So for tension members, obviously, tension members mainly support or resist tension forces. Okay, compression members mainly resist compression forces, while flexural members obviously mainly resist flexural flexural stresses that are induced by transverse loadings. Okay, so you can usually see transverse loadings coming from gravity loads such as dead loads and live loads. Different kinds of beams are used in structures such as girders for moment resisting frames, joists for floor systems, purlins for roof systems, stringers for floor and bridge deck systems, and lintels for doors and windows. So these are the most common places that you can see a flexural member or a beam or flexural member in general. So you can see usually a flexural member as a girder. Girder, what is the difference between a girder and a normal beam? So when we say girder, girders are usually moment resisting frames, meaning these are structural elements that resist moments. Okay, so usually when we model a girder, it will usually look something like this, a fixed-ended beam. And we know for a fact that fixed-ended beam has a moment on each end. Okay, so meaning this particular element resists moments on both of its ends. And that is an example of a girder. Or should I say, that is how we model girders. Okay, so when we say a beam, simple beam in general, it is just modeled as a simply supported like this one, where it doesn't resist moments on both of its ends. Just like a simply supported beam, 'di ba wala namang moment sa ano, sa end ng mga simply supported beam. Hindi naman siya nagre-resist ng mga moment, 'di ba, sa mga end niya. Ang nagre-resist ng moment sa mga end niya yung fixed-ended beam. Okay? That's why usually 'pag mino-model natin yung girder, this is how a girder looks like. Para siyang fixed-ended beam. While yung mga normal lang na beam, usually ganito yung pagkaka-model natin sa kanila, simply supported. Okay? Sa 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 mismong structure, or should I say, sa mismong structural plan, usually, saan ba natin nakikita usually yung mga girders? Usually makikita mo yan kapag yung support niya parehong column. Kunyari, ito column, tapos ito column. Tapos there is a beam that connects one column to the other. Pag ganyan, usually ang tawag natin diyan girder. Kasi ang assumption natin diyan, yung connection between the beam and the column ay fixed or rigid. Yan, yung connection na yan. Usually ang assumption natin diyan rigid. Kaya kapag minodel natin yan, yung ganyang configuration, ganito ang itsura niyan. Para siyang fixed-ended beam. Okay? Yung normal na beam, usually matatagpuan mo yan kapag yung support niya ay parehong beam din. Kunyari, ito, may beam dyan. Tapos may beam dyan. Tapos, merong nagko-connect sa kanila na another beam like this. Okay? So, ito, this is usually modeled as simply supported beam. Parang ganito. Okay? So, usually, yung connection niyan between this beam tsaka dun sa supporting beam, usually, ang assumption natin dyan, parang hinge or roller support lang. So, hindi siya nagre-resist ng mga moments. So, this is not a moment resisting frame, but this is a moment resisting frame. Okay, so that is the difference between a beam, yung normal na beam lang, and a girder. Okay? So yan, dyan natin usually nakikita yung mga beams as a girder, as joy, sa mga floor systems, purlins for roof systems. If you are familiar with purlins, ito yung, kumbaga sa Tagalog, pamakuan. Diyan pinapako yung mga bubong, usually. Usually, ang ginagamit natin na purlin ay mga C-shape or channel shape, mga ganito. Kaya itsura ng mga C-shape. Pa-letter C. Kunyari, meron kang bubong dito. Bubong. Makikita nyo yung mga bubong minsan may mga ganito. May mga porlina na tinatawag. So, dyan kinakabit yung mga ano, yung bubong, yung roof. Dito siya kinakabit yung roof. Ito. Yan. So, ito yung roof. Tapos, ayan, pinapako dyan or kinakabit kung paano man kinakabit yung roof na yan. Tornilyo or whatever. Okay. So, ito yung pinaka-support ng roof. Tapos, ito yung pinaka-roof. Yung this can be any type of roof, corrugated, or kahit yung flat lang, kahit aluminum. Pero usually, ganyan yung itsura niyan. Kung meron kang bahay like this, yan, simpleng bahay lang. Simpleng drawing lang ng bahay. So, itong pinaka-slope na to, ito lang din yan. Yan. Tapos, meron pa siyang ano doon. May mga perlina siya na nakakabit diyan, kung saan kinakabit yung mismong bubong, 'yan, parang ganyan. So, diyan kinakabit yung mismong bubong, mismong roof, okey. So, ang itsura niyan ng mga perlina na 'yan 'pag tinignan mo dito sa kumbaga ito kasi elevation view, eh. 'Pag tinignan mo sa top view 'yan, parang ganito ang itsura niyan. Para siyang beam lang, tapos meron siyang mga support dito, whether atras or another beam, 'yan. So, parang beam din ang model natin sa kanya sa mga perlina. 'Pag tinignan mo 'to sa top view, top view niya ganyan itsura, ganito itsura, okey. Ah, saan pa natin nakikita? Stringers, lintels. So, saan natin nakikita usually yung lintels? Yung mga pinto natin, 'di ba usually nasa mga wall 'yan. Kunyari ito isang wall, ta's 'di ba may butas 'yan dito para lagyan ng mga pinto or window. For this case ano na lang, pinto na lang. So, siyempre may mga ano diyan 'di ba may mga bricks or hollow blocks. May mga hollow blocks diyan, eh, kung saan gawa yung ano, eh, yung wall, 'yan ganyan. Maraming hollow blocks diyan, 'yan hollow blocks, hollow blocks, hollow blocks, 'yan. Hollow blocks ibig sabihin hollow, butas, may butas siya, okey. So, ganyan itsura niyan, eh. So, siyempre yung mga hollow blocks na nandito sa ibabaw nitong butas, kunyari ito, yung hollow blocks na 'to, if you will try to think of it, saan papatong yung ano na 'yan, hollow blocks na 'yan kung butas 'to, 'di ba? Siyempre 'pag pinatong mo yung hollow blocks na 'yan, since butas 'to, wala siyang tutuntungan, 'di ba? That's why naglalagay tayo ng tinatawag natin na lintel beam, 'yan. Medyo maliit lang na beam 'yan, parang ganyan, 'yan. Ganyan, 'yan, lintel beam 'yan kung tawagin. Para siya yung mag-support dun sa mga hollow blocks sa taas nung butas, whether window man 'yan or door. So, diyan niya ipapatong ngayon yung mga hollow blocks. So, may support na. May support na yung hollow blocks sa ibabaw ng mga butas na 'to sa mga wall. Okay, so obviously beam din 'yan. Kaya nga siya tinawag na lintel beam because it's a beam, okay. Beams carry both tension and compression stresses. As you have learned from strength of material, hindi lang ang beam, once na nag-bend 'yan, kunyari straight beam, once na nag-bend 'yan, it will look something like this. And from strength of material or mechanics of deformable bodies, you have learned na once na nag-bend yung beam, yung upper portion niya experiences compression. So, parang nako-compress yung mga fiber or yung mga hibla that compose the whole beam. And then yung mga fibers or hibla dito sa bottom or sa ilalim ng neutral axis, they experience what we call tension stresses or tension forces. Okay? So, nagbe-bend 'yan due to a transverse load. Every time na nagre-resist yung beam natin ng transverse load like this, when you say transverse, ibig sabihin, kung ito yung longitudinal axis, when we say longitudinal axis, it is the axis parallel to the longer side of the beam. So, yan yung longitudinal axis. So, when you say transverse, ibig sabihin perpendicular dyan sa axis na yan, sa longitudinal. Okay? That's why you are seeing here, naka-perpendicular siya dito sa longitudinal axis, which is usually the neutral axis din. Okay? So, every time nag-apply ka ng ano diyan ng load, kunyari simple supported beam lang 'to. Every time nag-apply ka ng load diyan, matik magbe-bend yung beam mo. And then once na nag-bend 'yan, it can experience compression on the fibers above the neutral axis, above this. So, dito 'yan banda. Itong portion na 'to, it can experience compression. Parang nako-compress yung mga fibers diyan, like this, yung tinuturo ko dito. And then yung ilalim, it can experience tension naman. So, parang nahahatak yung mga fibers niya diyan. So, therefore, ang beam, hindi lang siya nakaka-experience ng tension lang, just like sa tension members, or compression lang, just like sa compression members, but a combination of both. Okay? Combination ng tension and compressive stresses. Okay? So, there are many types of beams according to their support configurations. So, ito yung mga different types ng beam natin, depende sa kung paano sila sinusuportahan. Okay? So, katulad nitong cantilever beam. So, when we say cantilever beam, it's just a beam na yung support niya nasa isang end lang. And then the other end, walang support. Free. Free siya, wala siyang support. Okay? That is a cantilever beam. And then yung support niya dito, obviously, dapat fix. Kasi dapat mag-resist siya ng moment. Kasi pag di siya nag-resist ng moment, yung cantilever beam mo or yung beam mo lang, iikot lang siya with respect to this. Kung di nito pipigilan yung pag-ikot, di ba may tendency yan na umikot ng paganyan with respect dito. Dito sa ano na to, sa point na to. Parang gaganyan yung beam eh. Yan, no? Iikot siya ganyan eh. Kung hindi nagre-resist to ng moment, yung support na to. So para i-resist yung clockwise moment na yan, dapat merong counterclockwise moments dito. Para i-balance niya yan. Para hindi mag-bend or mag-rotate like this yung beam natin. Okay? So that's a cantilever beam. Isa lang yung support, pero fix. Tapos sa kabilang support, free. Ang simple supported naman, dalawa yung support on both ends, pero hinge or roller lang. Or in general, hindi siya nagre-resist ng moment. Hindi siya dapat nagre-resist ng moment. So pag ganun yung case, that is what we call simply supported beam. Yung overhanging naman, simply supported lang din to. Actually, dapat ano naman to eh. Dapat hinge man lang to, yung isa. Simply supported beam lang din yan yung overhanging beam. Ang nangyari lang, from simply supported, nag-extend ka lang dito ng span. Okay? So, may naka-overhang. That's why it's called overhanging. Okay? So, pwede siyang mag-extend on one end lang or on both ends. Just like what you are seeing here. Nag-extend siya on both ends. So, nagkaroon ng dalawang overhang. Okay? Continuous, parang simply supported lang din. Pero, ang pinagkaiba niya, nagkaroon ng intermediate supports. Yan, intermediate roller supports. And because of those intermediate supports, naging indeterminate yung beam natin. Okay? Ito, tsaka to determinate pa yan. Ibig sabihin, masosolve pa yan natin yan, yung mga unknown reactions dyan. Using simpleng statics lang. Summation forces, summation moment, zero. Solve pa natin yung mga unknown forces na yan, yung mga reactions na yan. Ito, indeterminate na to. Kasi, ilan yung unknown dito, supposedly? More than 3 na. Ayan, 4 nga dito eh. Actually, 5 pa yan. Kung merong horizontal force na apply dito, maglilima pa yan. So, determinate na yan. So, nagkaroon ng redundancy na tinatawag. So, nagkaroon ng redundancy dito sa point na to, tsaka sa point na to. So, yung dalawang support na to, redundant. So, when we say redundant, supposedly, hindi naman siya talaga kailangan. Pero, kumbaga, kahit tanggalin mo siya dyan, yung structure mo hindi naman guguho, it can still resist loads. So when we say redundant, ganun yung meaning niya. Kahit tanggalin natin siya dyan, imagine niyo tanggalin natin yung load na to, yung support na to. Tapos may in-apply ka na load. Can the structure still resist the load, the applied load? Yes. Kasi para magiging simply supported na lang siya eh. Okay, so ibig sabihin, redundant to. Redundant yung ano na yan. Yung dalawang support na yan. So yung mga redundant supports, hindi naman talaga siya kailangan totally. Pero syempre may purpose yan. Kaya siya nandyan. Okay, it serves a purpose lang. It serves other purpose. Okay, that's why nandyan siya. So ganyan yung continuous. Simply supported na nagkaroon lang ng intermediate supports. Okay, so continuous siya over this redundant supports. Okay, ibig sabihin ng continuous, I'll just delete some of the inks here. At di ko mapindot. Ayan. So when you say continuous, ibig sabihin, from this end, mapunta dun sa kabilang end, dire-diretso siya. Kaya nga siya continuous eh. Continuous, dire-diretso. Okay? Continuous siya over this supports that we have here. Okay? So when we say discontinuous, paano itsura ng ng discontinuous? Ang itsura ng discontinuous ay parang ganito. So from this end, punta ka dito sa redundant, tapos parang hindi siya tuloy-tuloy. So, putol siya diyan, parang ganyan. Tapos tsaka pa lang siya pupunta ulit sa kabilang support, tapos putol ulit. Hindi siya tuloy-tuloy, in other words. Kaya nga siya tinawag na discontinuous eh. Okay? So, parang meron siyang ano dyan, may discontinuity siya na tinatawag. May space ba? May space. Parang gano'n. Okay? So, that is what we call continuous beam. Yung fixed-ended beam, nabanggit ko na kanina, both of its supports, both of its ends may support, and yung support na yon ay fixed support. Meaning, it can resist forces as well as moments. Okay? Cantilever, simply supported, or prop beam, ang ibang tawag dyan, prop beam eh. Prop. Yan, prop beam. Cantilever beam lang din yan na may roller support dito. Roller or hinge support dito sa kabilang end. Okay, so that is what we call prop beam or cantilever supported beam. Cantilever simply supported beam. Okay? So ito yung mga ano nila, formal definitions nila ng mga binanggit ko. When we say simply supported or simple beams, pin or roller supports lang on both ends. Overhang, simple beams lang with overhangs on either one or both ends. Same lang sa binanggit ko kanina. Continuous beams, multiple simple spans with or without overhangs. Cantilever beams, beams composed of a fixed support on one end and free on the other end. Prop beams or the cantilever simply supported, beams composed of a fixed support on one end and at least one pin or roller support at any point along the beam, and fully restrained beams, which is this, beams with fixed supports at both ends, which may or may not have pin or roller supports at any point along the beam. So, pwede mong lagyan niya ng mga intermediate supports pa dito. Okay. Yung fixed-ended beam natin. Although pag ganun, pwede na nating tawagin na, na continuous beam din to eh. Anyway, most of the time, ganito na maitsura ng continuous beam. Usually, walang moment na nire-resist. Okay, so that is usually the different places or different types of elements that you can usually see a flexural member or a beam. Okay, so that is the definition of a beam. In analysis and design of beams, the following member limit states are to be considered. So ito yung mga chine-check natin usually whenever we design or analyze a beam or flexural member. So first, we usually check yielding. So what is that? It is the phenomenon in which the material starts to behave beyond its elastic range, i.e., the material starts to deform even without any additional load applied on it. For beams, yielding is significant by the formation of plastic hinges at some points along them. More detailed discussion of this phenomenon is discussed in topic 4.2 of this module. So yung yielding na yan, we are already familiar with we are already familiar with the definition of yielding. So we all know, kung babalikan natin yung stress strain diagram ng steel, 'di ba, straight line muna 'yon hanggang dumating sa proportional limit wherein 'yun yung limit kung saan it ceases to be elastic, meaning 'pag sinabi nating elastic, once na tinanggal mo yung load, babalik pa siya sa original form niya. Okay, yung kasunod ng proportional limit is yung elastic limit, halos magkakadikit lang 'yan. And then yung yield point na tinatawag kung saan kapag ini-stress mo pa siya beyond that point, it will behave ah, not inelastically na. Ibig sabihin hindi na siya babalik sa original form niya once na tinanggal mo yung applied load. Pag in-apply mo pa siya beyond that yield point. So kahit magkakaroon na siya ng tinatawag na permanent deformation. So pagdating niya diyan sa point na yan, kahit hindi mo siya dagdagan ng additional load, it will continue to experience an increase in strain, 'di ba? Strain to, 'di ba, yung x-axis. So makikita mo, same lang yung magnitude ng stress, pero yung strain nag-iiba-iba na, nag-i-increase, 'di ba? Strain 1, strain 2, strain 3, palaki ng palaki yung strain niya kahit hindi man nagbabago yung stress. Ibig sabihin ibig sabihin lang 'yan, on that particular magnitude of stress, the material continuously experience strain even without an additional load. Okay, so ibig sabihin nag-yield na siya. Okay, and then after that, at some point, tataas ulit yung strength niya. So hanggang dadating siya sa ultimate limit or ultimate strength, and then babagsak sa rupture strength na tinatawag. Okay, so ang material natin, ayaw natin na ma-experience to, yung yielding na tinatawag. Okay, that's why ginagawa nating limit state to, itong point na to. Yan, yung tinatawag natin na yield point. Okay, ayaw natin na lumagpas dyan yung stress na nararamdaman ng material natin. And so since ayaw natin na lumagpas diyan yung stress na nararamdaman ng material natin, edi we include it on our limit state. So check natin yung material natin with respect sa yielding. Dapat hindi siya mag-yield, dapat hindi siya lalagpas diyan sa yield stress na tinatawag na yan, sigma y or Fy. Pagdating sa steel, F yung gamit natin na symbol. Okay? So, check natin yan yung yielding. That is the first limit state that we usually check. And then after that, we also check the limit state of lateral torsional buckling. So, what is that lateral torsional buckling? It occurs when there is lateral deflection or buckling accompanied by twisting or torsion due to the compression portion of the cross section being restrained by the tension portion. Okay, so paano nagaganap yung lateral torsional buckling or ano ba yung lateral torsional buckling? So just to give you an overview, if you have a beam, kunyari simple supported beam, once na in-apply mo yan ng transverse load, uh, there is a tendency that it will buckle laterally. Ibig sabihin, pag tinignan mo siya sa top view, pwede siyang mag-bend or mag-buckle like this. So ito top view to. Yan. So, ibig sabihin nagkaroon siya ng lateral displacement. Kung ganito yung original position niya, napunta siya ngayon dyan. Nagkaroon siya ngayon nitong magnitude na to ng lateral displacement due to the application of some load, some transverse load. Okay? Ngayon, since lateral torsional buckling yan, hindi lang lateral movement yung naganap. Okay? It's a combination of lateral movement and torsional buckling. Ibig sabihin, pag tinignan mo yung cross-section mo, kung ganito originally yung orientation niya, tapos in-apply mo ng load, lalo na kung eccentric yung load mo, may tendency siya na mapunta dito. Ayan. So, nagkaroon na siya ng lateral displacement like this. Kasi from this position, napunta siya dyan eh. Nagkaroon na siya ng lateral displacement, tapos nagkaroon pa siya ng torsional buckling, umikot pa siya. Okay, so pwedeng mangyari yan sa mga flexural member natin, lalo na kung masyadong mataas yung load na ina-apply mo. Okay, so ayaw natin mangyari yan. Ayaw natin mangyari yan sa beam natin, sa flexural member natin. That's why we have added that as our limit state. So we usually also check that limit state, yung lateral torsional buckling na tinatawag. Okay, and then lastly, yung tinatawagan natin na local buckling. It is the instability of the section components, which are the flanges or webs of a flexural member. Local buckling is signified by the deflection of its section components. Okay, so paano naman nagaganap yung local buckling? So kung yung sa yielding ang nangyayari, yung member natin, masyado na siyang na-stretch beyond its yield strain. Ibig sabihin nagkakaroon na siya ng permanent deformation. Masyado na siyang na-stretch or nako-compress beyond that capacity of yield point, yield strength or yield strain. And then yung lateral torsional buckling, ganito naman yung nangyayari. Nagla-lateral deflection na siya, tapos nagbabakal pa siya, umiikot pa yung member. Sa local buckling naman, ang nangyayari, yung section components mo yung nagbabakal. Okay, so siya yung nalulukot kumbaga. So kung originally ganyan yung position niya, pwedeng mangyari sa kanya ganito. Pwedeng mag-buckle. Kunyari maging ganyan yung itsura ng top flange, tapos yung web gumanito, tapos yung yung bottom flange pwedeng gumanyan. So nagkaroon siya ng tinatawag natin na local buckling for a particular portion lang. For a particular portion along the beam. Okay? Or pwede rin naman maraming portion. Basta hindi siya yung buong ano, hindi siya yung, buong length ng beam. So, local lang siya, local. For a particular point lang. That's what we meant when we say local. For a particular point lang nagaganap yung backlink. Okay? So now, to have a knowledge, the required knowledge to study the limit state of yielding, let us have an introduction to plastic analysis of beams. So let us just have a quick review about the elastic flexure formula for beams. So from mechanics of deformable bodies, the flexural normal stress at any point on a beam cross section is determined to be equal to this. So I hope you can still remember this way back from mechanics of deformable bodies. So if we have a beam that already bended like this, and then if this is the neutral axis, so as I mentioned a while ago, the fibers above the neutral axis, which are this, the fibers above the neutral axis tends to compress. Okay, they tend to compress each other, while the fibers below the neutral axis, they tend to stretch out like this one. Okay, so because of that compressing and stretching, that results to what we call flexural stresses, which can be graphed with respect to the depth of the beam. So if this is the beam, this is the section. If this is it, if this is the part of the beam, okay. So this is a section of a beam, and if this is the neutral axis, from mechanics of deformable bodies, we have seen that the flexural stresses with respect to the depth of the beam look something like this. So these are the compressive stresses, while these are the tension stresses. Okay, so those are what we call flexural stresses, FB. Okay, so the formula for that is MC over I. M is the bending moment acting here on this particular section along the beam. C is the half of the depth. Although this is not always the case, hindi man siya laging half ng ano, ng depth ng beam. Ang C, ah, distance from the neutral axis to the extreme concrete, to the extreme fiber. Okay, so that's the definition of C. It is the distance from the neutral axis to the extreme fiber. Okay, so whether dito sa bottom or sa top. Okay, it just so happened for the case of a rectangular beam na yung distance from the neutral axis to the top or bottom fiber ay equal lang naman. Okay, and then I is the moment of inertia of the beam. So if the beam is a rectangular beam, rectangular in section, and this is the neutral axis, the x-axis, let's call that x-axis. So when we say I moment of inertia, it is the moment of inertia with respect to this axis. Usually, yan yung ginagamit natin na moment of inertia. Kasi nga, pag nag-bend ang beam ng pag ganito, nagbe-bend siya with respect sa x-axis. Kumbaga, dyan siya umiikot. Ayan, Ayan, dyan siya umiikot sa x-axis na yan. So, kung dito mo siya titignan sa elevation view na to, yung x-axis parang nandito lang. Para siyang tuldok lang. Okay, tas diyan umiikot yung beam natin. So, pag dito mo siya tinignan sa section view, parang ganyan yung direction niya. Diyan umiikot yung ano, yung beam natin. Okay, or baliktad yung ikot niya. Pag ganyan dapat, pag ganyan. Okay? So yan yung flexural formula from mechanics of the formable bodies. Just a review. Just a review of the bending stress formula. Where FB is the flexural normal stress at a point located at a vertical distance C from the neutral axis of the beam. M is the bending moment acting at the given section or at the given beam cross section, and I is the moment of inertia of the beam cross section. From the formula, it can be determined that the maximum flexural normal stresses occur at the points that are farthest from the neutral axis, where C is maximum. Okay, the formula for the maximum flexural stress may also be written as this formula. So itong formula na to, tsaka ito, pares lang yan. Okay? So from this drawing, you can already interpret that the maximum flexural stresses occurs either on the top of the or the bottom fiber. Okay, kasi triangular in shape yan eh. So kung medyo gagandaan ko pa yung itsura ng drawing, so ganito yung itsura niyan. Triangular in shape, ito yung mga compressive stresses. Sa bottom naman, mga tensile stresses. Kung ito yung beam natin. Okay? Yan. Kung ito yung portion ng beam natin, ito hinge support. Yan. Tapos ito yung neutral axis. So makikita mo sa graph pa lang, yung maximum value ng flexural stress nandito nag-occur sa top tsaka sa bottom. Okay? Top and bottom. Yung sa top, compressive. Kasi paturo siya dun sa sa section ng concrete natin eh. Yung sa baba naman, tension yan kasi away. Papalayo siya dun sa sa concrete or sa section natin, sa beam natin. Okay? So the maximum values occur with either on the top or bottom fibers. Okay? So ang formula nun ay MC over I. For this case, sa rectangular section na to, equal lang yung magnitude nung stress dito sa top tsaka sa bottom. Kasi parehas lang yung I nila, obviously, kasi isang section lang naman yan. Yung bending moment, isa lang din, kasi isang bending moment lang naman yung nag-act sa buong section na to. And then yung C, since equal lang naman yung distance from the top tsaka sa bottom, di equal lang din yung C-top, yung C-top na tinatawag, C sub top tsaka C sub bottom. Yan yung mga distance from the neutral axis to the top or bottom fiber. So parehas lang ng magnitude yan. So kung parehas lahat yan, edi parehas lang yung bending stress dito sa top tsaka sa bottom. Although that is not always the case kasi kung hindi symmetrical yung yung beam mo, kunyari for the case of a T-beam like this. Kung nakakita na kayo ng mga T-beam, pa-letter T. Yan. So pag ganyan, usually hindi equal yung distance from the neutral axis tsaka sa bottom fiber tsaka sa top. Okay? So hindi laging equal guys ha. Ngayon lang nag-equal kasi nga rectangular yung section natin. So itong formula na to can be expressed using this notation wherein yung S natin dyan, yung section modulus na tinatawag, ay equal sa I over C. So yung C over I dito, gawin mo lang M over I over C. Kumbaga binaba mo lang yung C. Nilagay mo lang yung C sa ilalim para maging I over C to. Kasi pag sinimplify mo naman tong I over C, magiging MC over I din naman to, di ba? So yung I over C na yan, palitan lang natin ng S. Yung tinatawag natin na section modulus of the beam cross-section. It should also be noted that the section modulus may differ for the values of C measured to the top and to the bottom parts of the cross-section. So yung S natin na yan, meron yung tinatawag na S top tsaka S bottom. Kasi nga, simply because yung C nga, pwedeng magkaroon ng magkaibang value. Okay? Pwede magkaroon ng C-top tsaka sa C-bottom. If in the case na hindi equal yung distance from the neutral axis to the top or bottom fiber. Katulad nga nung sa case ng T-beams. Okay? So kung magkaiba yung C-top tsaka C-bottom, malamang magkaiba yung I over C for the top using the C-top and I over C using the bottom, the C-bot. So with that, magkakaroon ng S-top tsaka S-bottom. Okay? So, hindi laging equal yung S or yung section modulus ng mga beam. Depende yan sa C, sa distance from the neutral axis to the extreme fiber. Considering that it is possible for a beam to bend in two principal directions, the total flexural normal stress at any point on the beam cross-section is equal to this formula, where it considers stresses due to bending about major axis or about the minor axis. So, kapag biaxial bending, if you already heard biaxial bending. When you say biaxial bending, yung beam mo hindi lang siya ah, nagbe-bend with respect sa x-axis. But nagbe-bend din siya with respect dito sa y-axis. Yan, umiikot din siya diyan. Okay? So may mga ganong cases. So paano yung itsura nun? Usually ganito yung itsura nun. Paano ko ba ipapa-imagine? So ganito yung itsura niya pag sa side view. Yan, kunyari simple supported beam Ganyan itsura niya sa side view. Ta's 'pag tinignan mo siya sa top view, ganito pa yung itsura niya. If you can imagine kung paano nangyari yan, okey. So, ibig sabihin nag-bend na siya like that with respect dito sa x-axis, nag-bend na siya ng paganyan. Tapos with respect pa sa y-axis dito, nag-bend pa siya ulit. Yan, nag-bend pa siya ng paganyan. So, sabay sila nagbe-bend. Nagbe-bend ka na sa x-axis, nagbe-bend ka pa sa y-axis. So, ang bending na nangyari ay biaxial bending na tinatawag. So, when we say biaxial, bi, tsaka axial, ibig sabihin ng bi, dalawa. Axial or axis, dalawang axis. So, ibig sabihin, nagbe-bend ka with respect sa dalawang axis, x tsaka sa y-axis. Okay? So, with that case, hindi na basta MC/I yung formula. For the stresses, being experienced by the member like this, hindi na siya basta MC/I. So, nag-iba na yung formula because the stresses that the fibers experience on every portion here of the structural element or the beam, yung mga stresses na nararamdaman niya diyan at each portion, it's already a combination of the stress due to the bending about the x-axis as well as the bending about sa y-axis or bending about the major or minor or major and minor axis. So may end dapat. Okay. So kung gusto mong kunin yung biaxial bending stress, all you need to do is sum up the stress about the major axis or the x-axis and the bending stress due to the bending about the y-axis or the minor axis. Okay, MC/I plus MC/I lang din. With respect sa major tsaka sa minor, add mo lang yung stresses due to them, yun na yung total stress. Yun na yung total stress being experienced by the particular fiber. Kunyari itong fiber na 'to or ito na lang yung top fiber na 'to, okay? So that is just a recap of the elastic flexure formula for beams. So why did we have recap that? Because we need that concept for us to be able to understand the behavior of structural steel beams beyond the elastic range. Okay? So yung mga formula kanina, yung MC/I, applicable lang yun guys if the stress that the material, the steel experiences ay hanggang dito pa lang. Hanggang dito pa lang sa may bandang, proportional limit or elastic limit. Okay, ibig sabihin yung stress niya nararamdaman hanggang diyan pa lang. Okay, hanggang sa proportional limit. Elastic pa siya, ibig sabihin once na tinanggal natin yung in-apply na load, babalik pa siya dun sa zero strain dito. Gaganyan siya, 'di ba, umaakyat siya unti-unti. Akyat yung graph. Once na tinanggal mo yung load that causes this stress, babalik siya diyan. Babalik siya dito sa zero strain. Ibig sabihin elastic pa siya. Okay? So, yun yung elastic range na tinatawag. Ngayon, ang problema diyan, yung steel natin 'pag na-stress siya beyond the proportional limit or the elastic limit, ibig sabihin umaabot na dito yung ano niya, umaabot na diyan 'no, umaabot na diyan yung stress na nararamdaman niya hanggang yield or FY na tinatawag, hanggang yields. Ano na yung magiging behavior ng member natin or ng steel beam natin. Okay, so yun yung, aalamin natin for this topic. Assuming that the beam has adequate lateral stability, the beam may only fail due to yielding. It is usually assumed in design that structural steel is an idealized elastoplastic material, meaning once it reaches its yield point, it will not carry any more additional stress. For beams, it can be assumed that FB max or the maximum bending stress is just equal to Fy. Okay, so nabanggit natin yung tinatawag na lateral stability. So very important kasi ang lateral stability na yan para ma-attain ng steel beam natin yung yielding niya. So ano ba yung lateral stability na tinatawag? Yung mga beam natin, kunyari simple supported beam like that. Di ba nagbe-bend yan like this. Okay? Para hindi siya maka-experience ng biaxial bending na tinatawag, para hindi siya magkaroon ng torsional buckling whatsoever. Usually naglalagay tayo ng mga adequate lateral support. So anong itsura ng mga lateral support na 'yon? So kunyari 'pag tinignan mo 'tong beam na 'to sa top view, yung lateral supports na 'yon, it can come in many forms. So pwede siyang bracing line like that, kumbaga parang may nakatungkod lang diyan. Top view 'to, Puwede siyang maging ganyan, may lateral bracing siya dito sa point na 'to tsaka sa point na 'to, puwedeng ganyan or puwede ka pa ngang magdagdag ng lateral bracing dito sa gitna, okey? Just to prevent the beam on buckling or deflecting on both sides. Para hindi siya mag-deflect dito sa side na 'to or dito sa side na 'to. Para 'pag nag-bend siya, diretso lang siya magbe-bend like this, okey? Hindi siya magbe-bend ng 'pag ganito pa. Kumbaga nagbe-bend na siya ng like ng katulad niyan tapos magbe-bend pa siya sa on the other axis. Para mapigilan 'yan, to prevent that, maglalagay tayo ng tinatawag natin na support, adequate lateral support, okey? Para ma-achieve niya yung ano niya, yung yielding niya, okey? So, ang assumption natin diyan sa steel member natin, elastoplastic material siya. When we say elastoplastic, once na naramdaman niya na yung yield stress na na property niya, once na nakarating na dito sa stress na 'to, yung stress na nararamdaman niya, it will no longer carry any more additional stress. Okay, kumbaga 'yan yung ginagawa nating limit, 'yan yung failure kumbaga na sinasabi natin. Once na nakarating na siya diyan sa point na 'yan, hindi na siya magre-resist ng stress larger than that. That's the behavior of elastoplastic material. Okay, so meaning lang nun guys, yung maximum bending stress na kaya niya lang i-resist ay equal sa Fy, yung yield stress na tinatawag, hanggang dito lang. Hanggang diyan lang yung maximum value nito. Nung kanina yung dinrawing ko na dalawang triangle, eh, 'di ba ganito yung itsura ng flexural stress, 'yan. Andali, pangit na naman ang drawing ko, eh. Ayusin natin, ah. Ito pala may drawing na pala dito, eh. 'Di ba yan yung sinasabi ko kanina, yung mga bending stresses na 'yan, 'yan. Yung maximum value lang niyan nung mga bending stresses na 'yan hanggang Fy lang. Sabihin yung haba niyan, 'yan yung magnitude niyan, hanggang Fy lang. Okay, that's the behavior of elastoplastic material. So, any magnitude of stress larger than the Fy hindi na ire-resist nung section. Hindi niya naire-resist, magfe-fail na lang siya. Magfe-fail, mag-aano na lang siya, mag-yield, magkakaroon na lang ng ano, permanent deformation, et cetera, et cetera. Yielding occurs first at the farthermost fiber in which it will not carry any more stresses. Definitely yung yielding guys nangyayari dito sa outermost fiber, either sa top or sa bottom fiber. Simply because dun nga nagaganap yung maximum stress, ayan, either sa top or sa bottom, dun nagaganap yung largest magnitude of the stress. So, meaning, yung unang-unang makakaramdam ng Fy, if ever na makarating na sa magnitude of Fy yung stress na nararamdaman ng beam mo, yung unang-unang fiber na makakaramdam niyan, yung nasa taas. Kasi nga, siya yung malaking nagre-resist or siya yung nakaka-experience ng pinakamalaking bending stress, yung nasa taas. Kasi nga, the bending stress varies linearly lang as you go to the neutral axis. Like that. Babari lang siya linearly. Okay? The bending moment that causes yielding at the farthermost fiber is called the yield moment. So yung bending stress na naka-apply dito sa beam natin na 'to, that resulted to the stresses like this, yun yung tinatawag natin na yield moment, okay? Kasi hindi naman magkakaroon ng ano, ng mga stresses kung hindi nag-bend yung beam, 'di ba? Kung straight lang yung beam mo, walang ano, walang bending stresses kasi nga bending stresses nga siya, meaning nag-o-occur lang siya once na nag-bend yung beam mo. Once na nag-bend yung beam mo, makakaramdam niya ng mga bending moment. Bending moment na yun, yun yung reason bakit nai-stress 'to, bakit nagkakaroon ng stresses sa section natin. So yung moment na yun, yan katulad nito, kunyari simple supported beam, kinuha natin kunyari yung moment dito sa gitna, somewhere here. Yung moment na makukuha natin diyan that cause that cause this flexural stresses equal to Fy on the outermost fiber of the beam. Ang tawag natin diyan ay yield moment, My. Okay? So paano makuha yung My na yan? 'Di ba ang formula for bending stress? Fb is equal to mc over I. Okay? So kung yung FB mo is already FY, kung hahanapin natin yung M that will cause a stress, a bending stress equal to Fy, therefore, we can already call that M as My. Okay, so yan yung My or yield moment na hinahanap natin. Gawin lang nating Fy to, hanapin natin yung corresponding value ng My. That's already, corresponding value ng M, that is already My, the yield moment. Okay, so kung naka-express as bending moment equal to M over S, kung ganyan yung expression mo ng bending moment instead of MC over I, kung ginawa mong S yung I over C, kung kukunin natin yung My, it will be equal to this. So, move lang natin yung S doon sa kaliwa. Tapos, may ganito yung formula. FBS. M is equal to FBS. Palitan natin ng Fy to. Yung makukuha nating product between Fy and section modulus, that is already the yield moment My, which is equal to this formula. Okay, so yung sinabi ko na dyan, tsaka ito, pares lang yan. Okay, as more load is applied on the beam, the other fibers will also reach yielding until it reaches the point where all of the fibers at the cross section becomes plastic. The bending moment that makes this happen is called the plastic moment. So, nasa ganyang point na, yung ano natin, yung stresses sa beam natin, wherein yung bending stress niya equal na sa Fy. Kanina, nung elastic pa siya, yung variation ng flexural stresses natin ganito pa. Okay, ibig sabihin, yung moment na nararamdaman niya, mababa pa. Hindi pa siya kasing laki ng My, yung yield moment. So, therefore, yung flexural stresses na nararamdaman at the depth of the whole cross-section, mas maliit pa kaysa sa Fy. Hindi pa siya nag-yield eh. Pero once na nag-equal na yan, once na nag-equal na yung flexural stress sa yield stress, ibig sabihin lang nun, yung moment na nararamdaman ng cross-section ay equal na sa yield moment sa My. Yung moment that will result to a stress equal to Fy, the yield moment. Okay? So, paano nakakarating yan from this flexural stress to this flexural stress? Mangyayari yan guys kung lalakihan mo yung bending stress. Lalaki mo yung bending stress or bending moment, sorry. So, paano lumalaki yung bending moment? Eh, di kapag tinalakihan mo yung yung transverse load na kini-carry ng beam, lumalaki yung yung bending moment. Kunyari dito, kung ang in-apply mo lang diyan ay 10, ano yung magiging magnitude ng moment sa midspan? So, meron siyang corresponding value, di ba? Pero once na nilakihan mo yung applied load diyan, ginawa mong 20, di ba yung moment mag-increase din? Okay, kunyari 10 din to, tapos ito magiging 20. So, lalaki yung moment. Once na ini-increase mo yung applied load. Okay. So, kunyari, ini-increase mo yung load, kunyari, kanina 10, ito yung flexural stress distribution. Nung in-increase mo to 20, naging ganito na yung flexural stress distribution. Makikita mo lumaki yung mga bending stresses. Yan o, yung haba. Yung haba niya dyan, mas lumaki. Ibig sabihin, lumaki yung niyan, yung flexural stress. Yung bending moment that causes this flexural stress distribution, yun nga yung tinatawag natin na yield moment. Okay. Ngayon, pag tinaasan pa natin yan, yung magnitude ng force na yan, na ina-apply natin, ginawa natin 30. So, lalaki pa yung bending moment dyan. Kunyari, magiging 30. So, lalaki pa yung bending stresses din. So, magsusunod-sunod yan eh. Diba? Magsusunod-sunod yan. Lalaki pa supposedly. Lalaki pa supposedly yung bending stress. Supposedly, ganito yung magiging yung bagong flexural stress distribution. Pag ganyan, mas malaki pa. Makikita mo, mas humaba pa siya. Kung nag-increase tayo ng moment Pero since yung stress na nararamdaman dito sa fiber na 'to at this stage, Fy na. Sabi nga natin ang steel elastoplastic material, ibig sabihin hanggang Fy lang yung kaya niyang i-resist. So ang mangyayari diyan, supposedly ganito kalaki yung stress sa top fiber, pero hindi na kayang i-resist ng steel section niyan. Ang ire-resist niya lang is yung Fy lang, hanggang Fy lang. Okay? So supposedly ganyan yung natin, yung bending stress distribution. Yan, ganyan. Pero since elastoplastic material nga yung natin, steel natin, hindi niya kayang i-resist tong buong 'to. Yan. Ang kaya niya lang i-resist itong portion lang na 'to hanggang Fy lang. Okay? So Fy hanggang Fy lang yung nare-resist na stress nung steel section natin. Okay? Once na in-increase pa natin yung bending moment niya. Okay? So since yung stress dito sa portion na 'to, sa fiber na 'to is mas malaki na kaysa sa Fy, you can expect dito until dito sa portion na 'to, yung mga stress na 'to, mas malaki pa sa FY meaning nag-fail na yung mga fibers hanggang dito sa portion na 'to, ayan, oh. Yung mga fibers above this portion nag-fail na, ibig sabihin ang nararamdaman na nila na stress ay FY. That's why makikita mo dito constant na yung stress. Kasi from this fiber to that fiber, eto, ang nararamdaman na nila na stress ay FY na, hanggang FY na. So, ibig sabihin fail na sila. So, unti-unting nagfe-fail yung mga fibers ng cross section mo habang ini-increase mo yung moment. In fact, kapag in-increase mo na naman yung moment diyan or should I say, pag in-increase mo na naman yung load diyan, ginawa mo 40, so maglalaki na naman yung moment, magiging 40 kunyari. So, ang mangyayari dito sa stress distribution, magbabago na naman 'yan, lalong lalaki na naman supposedly yung yung stress distribution natin. Dapat magiging ganito na siya, parang ganyan. 'Yan, sobrang lalaki na siya dapat. Pero since yung material natin hanggang FY lang yung kaya niya i-resist, ang mangyayari lang diyan, yung slope nitong ano na 'to, nitong line na 'to, 'yan, yung slope nito, ang mangyayari lang diyan sa load distribution natin habang lumalaki yung moment or consequently yung stress, ang mangyayari diyan sa slope niyan, liliit ng liliit yung slope niyan. Kumbaga nakita niyo naman yung trend, eh. Kanina yung slope niya ganito, tapos naging ganito yung slope, ta's naging ganito na yung slope. So, ang ultimate point niyan is yung slope niya horizontal na. Ayan, oh, katulad nito. At 'pag nag-horizontal na yung slope ng load distribution, ibig sabihin lang nun, mula sa fiber na 'to hanggang dito nag-fail na, pare-parehas FY na. Pare-parehas na FY na yung stress na nararamdaman nila diyan. Okay, so that's the time that we can say na naramdaman na nung section natin yung tinatawag na plastic moment na tinatawag. So, ano yung plastic moment na yun? That's simply the bending moment that cause the stress, I mean, that is simply the bending moment that cause the section of the steel to experience stress equal to FY for the whole depth of the cross section. So, makikita mo dito, buong depth ng beam natin, puro FY na yung nararamdaman niya na stress. Although dito sa upper portion, siyempre compression, sa baba tension. Pero FY pa rin naman. FY pa rin naman yung magnitude niya. Okay? So yung bending moment that caused that scenario, yun yung tinatawag natin na plastic moment. Plastic moment. Yun yung kumbaga ultimate failure scenario na sinasabi natin na ayaw nating maramdaman ng beam natin. Kasi pag ganyan na yung nararamdaman ng beam natin, buong section niya failed na, buong section niya nag-yield na, diyan magaganap yung tinatawag nating plastic hinge. Magaganap yung plastic hinge na tinatawag, which is this. So ano yung plastic hinge na yan? As the plastic moment is reached, a plastic hinge forms at that point in the beam. For a statically determinate beam, a plastic hinge is considered as an internal hinge which would make the beam unstable. This instability caused by the formation of a plastic hinge is known as the collapse mechanism. So yan nga, kunyari puro yield stress na yung nararamdaman nung beam on that particular section because of the applied moments or because of the applied loads that cause the bending moments corresponding to plastic moment. Kapag puro FY na, puro yield stress na yung nararamdaman ng buong cross section, katulad nung kanina, may mabubuong tinatawag nga natin na plastic hinge, which is this. So para kang nagkakaroon ng internal hinge for the case of determinate beam. So ano ba yung nangyari diyan kung magkakaroon man ng plastic hinge? Anong pake natin diyan? Ano naman kung magkaroon ng plastic hinge? So kung nai-imagine niyo anong mangyayari sa isang simply supported beam na nagkaroon ng internal hinge dito, if you can imagine what will or how the beam will behave. Kunyari, in-applyan ko siya ng load like that. Can you imagine kung kaya pang mag-bend man lang nung beam natin? Hindi na magbe-bend yung beam natin. Kasi since may hinge siya dyan, so it can freely rotate. It can freely rotate with respect to that plastic hinge. So, since roller pa to, ang mangyayari dyan, once na bumaba yan, hahatakin niya lang. Yung beam, hahatakin niya lang yung roller, dadaustos lang yan. Pag nag-rotate to. Due to the applied load here. Hindi siya katulad ng normal na simple supported beam like that, na in-apply mo ng load tapos magbe-bend lang, 'di ba? Magbe-bend lang yung beam na 'yan, ganyan. Kasi may resistance pa, may stiffness pa. May stiffness pa yung beam mo, so magbe-bend pa siya like that. Unlike dito, wala ng resistance, talagang follow na lang siya. Magfo-follow na lang siya sa dinikta nitong applied load na 'to. So, in-apply mo siya, gusto mo mag-deflect, hindi na lalaban. Hindi na lalaban yung beam mo. Kumbaga ano na lang, tutuloy na lang siya magde-deflect. Unlike dito sa simply supported beam na walang plastic hinge or internal hinge, in-apply mo siya ng load, lalaban yung beam mo. Lalaban yung beam mo. Ire-resist niya yan. Merong internal forces na magre-resist nung ano, nung applied load na yan, which are the shear and bending moment. Okay? Merong internal forces doon na magre-resist yan. Dito wala. Walang magre-resist na moment, na bending moment inside the plastic hinge. Kasi nga hinge siya, 'di ba? 'Di ba alam naman natin pag hinge walang moment, walang moment na nire-resist. Di niya kayang pumigil ng rotation. That's why nagro-rotate na lang siya like that, 'di ba? From the original position na horizontal, nagro-rotate na lang siya ng paganyan. Yan, at a certain angle. Okay? So yan yung iniiwasan natin guys whenever we design beams. Yung dumating siya diyan sa point na mag-produce siya ng tinatawag natin na plastic hinge. Kasi yung formation niya ng plastic hinge na yan, that will be what we call the collapse mechanism wherein the beam will already collapse. If you can imagine ano mangyayari sa beam natin na 'to, magko-collapse yan of course, 'di ba? Actually kung masyado pang malaki yung applied load na yan, ang ultimate na itsura ng beam na yan na pinapakita natin parang ganito na, parang magaganyan na, halos magdidikit na yung ano, yung hinge tsaka roller. Halos magdidikit na yan ultimately kung sobrang lakas ng ano, sobrang laki nung ano, in-apply mo na load dito. Kasi dito puwede pa rin siya mag-rotate, eh, kasi roller lang naman yan pati dito, eh. So, free to rotate siya diyan ta's magdagdag ka pa ng hinge dito. So, wala na talagang rotate-rotate na yung mga yan. So, that's actually a collapse mechanism or a failure na ayaw nating maramdaman ng beam natin. That's why we are designing our beam in such a way that it will not experience plastic hinges. Hindi siya magfo-form ng plastic hinges, hindi siya makakaramdam ng plastic moment. Okay? So, that is how we design the beam. Dapat hindi siya dumating dun sa point na yon na it will already form plastic hinges, or in other words, it already experienced the plastic moment na tawag natin. Okay? So, iniiwasan natin yon. So, para maiwasan natin yon, syempre dapat we know what is the particular magnitude of that plastic moment. Okay? Nang sa ganun, mapaghandaan natin siya. Nang sa ganun, malimit natin yung ma-apply natin na load and the cross-section and everything para hindi siya dumating sa point na yon na makakapag-form na siya ng plastic hinge simply because nag-fail na totally yung buong cross-section. Okay? So, we have to compute for that plastic moment. And for us to compute for that plastic moment, dapat malaman natin yung tinatawag natin na plastic modulus. Kasi, paano ba nakukuha yung plastic moment? 'Di ba bending stress is equal to M over S. So, para makuha mo yung plastic moment, kailangan mo ng parameter, bending stress, tsaka section modulus. Kailangan mo ng section modulus. That's why we have to find a way how to compute for that. Yung tinatawag natin na plastic modulus. Okay, so that will be the next topic. The determining of the plastic modulus and shape factor of a beam cross section. The plastic moment is determined by drawing the stress distribution of the beam cross section at its fully plastic state. So, ito yung steel section natin at ito yung neutral axis niya or yung plastic neutral axis na tinatawag. Yung plastic neutral axis tsaka yung neutral axis, yung usual na neutral axis na sinasabi natin. Hindi sila laging parehas ng location. Okay, hindi sila laging parehas ng location. Anong pinagkaiba nila? Yung neutral axis, nandun siya sa centroid nung cross section. Nandun siya sa geometrical center, geometric center nung cross section. While yung plastic neutral axis, nandun yan sa point kung saan yung compressive force due to the yield stress dito upper portion ng beam tsaka yung tensile force dito sa lower portion niya nag-balance, okey. So, kung saan yung line na 'yan, yung point na 'yan kung saan nagba-balance 'tong upper tsaka lower portion na 'to, nandun yung tinatawag natin na plastic neutral axis. So, yung point na 'yan kung saan nagba-balance 'tong upper tsaka lower portion, hindi naman lagi yang corresponding sa gitna or sa centroid nung cross section, okey. So, kapag siyempre 'pag iba yung itsura ng section mo, don't expect sa magko-coincide yung neutral axis tsaka yung plastic neutral axis. Kung hindi symmetrical, kung hindi regular yung shape niya. Dito sa example natin, since regular naman siya, symmetrical, so expect mo yung neutral axis tsaka yung plastic neutral axis malamang talaga mag-o-overlap yan. Just like what happened here. Okay? So kung ganito na yung itsura ng stress distribution dun sa section natin, so ibig sabihin yung stress dito puro Fy na sa upper portion and then gano'n din sa lower portion. And then going back from mechanics of the four movable bodies, since we know that normal stress is just equal to force over area or simply force is equal to stress times area. So kung gusto natin kunin yung total force nito, yung total force coming from these stresses being experienced by the cross section of the steel beam. Kung gusto natin makuha yung resultant niyan, which is this, tawagin natin na C. All we need to do is multiply the stresses dun sa cross-sectional area on that particular region lang. Ito lang 'yan, yung cross-sectional area na 'to. Kasi diyan lang naman nag-a-act yung ano, yung compressive stresses, eh, 'di ba? Kunin mo yung area niyan, that is what we call the AC, area in compression, multiply mo siya dito sa Fy, sa magnitude nito, makukuha mo na yung total force, which is the resultant of these many stresses that you are seeing here. And same goes dito sa tensile stresses. Paano mo makuha yung total stresses or paano mo makuha yung total tensile stresses? All you need to do is multiply the magnitude of Fy to the tensile area. Okay? So, ito yung tensile area natin, yung lower portion. So, again, hindi laging equal yung dalawang yan. It so happens symmetrical yung sample natin dito, kaya nag-i-equal. Okay? So, ito, tawagin na lang natin yung area, yung blue, as the tension area, 80, and then multiply mo sa Fy. So, that is how you can compute for the total compressive and tensile stresses. Or simply, gamitan mo na lang ng ano, ng yung technique na ang pagkuha ng resultant ay equal lang sa volume nung diagram, nung load distribution or stress distribution or diagram. 'Di ba 'pag tinignan mo yung stress distribution dito sa section na 'to, it will actually look something like this. So medyo gagawin kong 3D view, Kung ito yung upper flange with the web. So ganito yung itsura ah, ng ah, ng stresses diyan. It will look something like this. Para siyang may volume. Yan. Tapos gano'n din dito sa ano, sa lower portion. So medyo hindi lang maganda masyado yung drawing ko, pero I hope na-imagine niyo. Yan. Paganyan yung ano niya, yung stress diagram. So kunin mo lang yung volume niyan. So paano ba makuha yung volume niyan? Dimension nito multiplied by dimension nito by dimension nito. Tapos gano'n din dito sa may web, sa web portion. Or in other words, parang ano lang yan, length times width times height. Okay, kunin mo yung volume nung sa flange, tapos i-add mo dito sa volume nung sa web, portion ng web. That will be the total force acting on that particular area. Okay, so kung medyo ayaw mo ng ganun, edi tandaan mo na lang 'tong formula na 'to. Area in compression times the stress. Okay? The tension and compression forces occurring on the cross-section should be equal to maintain static equilibrium, i.e. C is equal to T. Siyempre, dapat in equilibrium yan. Kasi kung hindi yan in equilibrium, magkakaroon tayo ng dynamics. Magkakaroon ng motion. Di ba yun naman yung result kapag hindi nagkakaroon ng equal forces? The result of unequal or an unbalanced force is motion. Di ba? Kung naalala nyo sa dynamics of rigid bodies, once na nagkaroon ka ng unbalanced force, magmo-move yung something na yon kung saan nag-a-act yung mga forces along the direction similar to the governing force. Kunyari meron kang, certain body diyan, in-apply mo ng magnitude of force na pa ganito, tapos force na ganito. So, magka-counteract yung dalawang force na yan. Pero since mas malaki 'to, the ball or kung ano man 'to will move on the same direction as this, kasi siya yung maggo-govern, 'di ba? So, kasi nagkaroon ng unbalanced force. Okay, hindi na kinayang i-balance nito yung force na 'to. Hindi niya kinayang i-balance. So, yung natira, yun yung magko-cause ng motion. Okay? So, dito sa case na 'to, siyempre ayaw natin magkaroon ng motion. So, dapat C is equal to T. Compression force is equal to tensile force. From here, it can be implied that the location of the neutral axis of the cross-section at its fully plastic state is not necessarily the same at its elastic state. Yan yung binabanggit ko kanina na hindi naman parehas yung location ng neutral axis sa plastic neutral axis. Okay? This new axis is now called the plastic neutral axis. From the static equilibrium equation earlier, the location of the plastic neutral axis may now be determined. Additionally, the plastic neutral axis divides the beam cross-section into two equal areas. The plastic moment is defined to be equal to this. Yan. So that is the formula for finding the plastic moment, which is the moment that cause the whole cross-section to experience a constant magnitude of stress equal to Fy. So sa nakuha yan, galing lang din yan dito sa bending stress formula. So kung yung FB mo or yung bending stress mo equal na sa Fy, and then yung M mo that cause the cross-section to experience Fy constant whole to the whole depth of the cross-section, that's called that MP, the plastic moment. And then yung section modulus corresponding to the plastic moment and the Fy is now called Z, the plastic modulus. Okay, so kung ayusin mo lang yan, in terms of MP, kuhain natin siyang MP is equal to Fyz. So, minultiply lang to dito. So, that is the formula for finding the plastic moment. Where MP is the plastic moment, Fy is the yield strength of the bib material. Z is the plastic modulus of the beam cross-section. Yan nga, kakabanggit ko lang. Since MP can be determined using a static equilibrium, the plastic modulus can be determined by dividing the plastic moment by the yield strength. Obviously, based on the formula. Kung given ka ng MP, tapos may Fy ka pa, paano mo makukuha yung plastic modulus? Eh di MP divided by Fy lang. Okay? The shape factor of the cross-section is defined as the ratio of the plastic moment to the yield moment. It should be noted that the plastic moment is always greater than the yield moment, thus making the shape factor always greater than 1. It can be determined using this formula here, where the Greek letter I don't know if this what is this Greek letter, epsilon. I think this is not epsilon. So, yung Greek letter na to, this is what we call the shape factor. Shape factor is the ratio of MP and My, plastic moment and yield moment. So, obviously, from the figure that I have mentioned or showed a while ago, obviously, MP is greater than always sa My. Kasi nga, ito yung ultimate na event eh. 'Di ba? My, sa simula, nag-yield pa lang yung yung portion ng cross-section natin. Pero yung MP, kapag MP na yung magnitude ng moment, hindi na lang portion nito yung nag-yield, kundi yung buong cross-section na. Okay, so obviously, palagi mas malaki yung MP tsaka yung My. But since ang shape factor is ratio ng MP and My at lagi mas malaki yung numerator sa denominator, expect mo yung shape factor natin usually greater than 1. Kasi nga, palagi mas malaki yung numerator. Okay, so that is the formula for shape factor. Ratio mo lang yung MP tsaka yung Y. Or if you will substitute the formula for MP, which is equal to Fyz, and then substitute din natin yung formula for Fy, which is equal to Fys. Cancel lang yung Fy, matitira is Z over S. So that is another formula for finding the shape factor. So kung alam mo na yung plastic section modulus tsaka yung section modulus, you can already you can already compute for the magnitude of the shape factor which is equal to this. I don't know what is the name of this shape. This is a Greek letter. I'm not familiar with the name of this particular Greek letter. Okay, so just to have an exercise on how to compute the plastic modulus and the shape factor of a rectangular section, let us have this sample problem. Suppose that a beam has a rectangular section oriented such that the longer dimension of the rectangle is parallel to the bending direction of the beam. So medyo nakakalito yan. Kailangan medyo familiar ka yan sa mga salita-salita na yan. So sabi niya, meron kang rectangular beam. Yan. Ang orientation niya daw is such that the longer dimension of the rectangle is parallel to the bending direction of the beam. So, paano yun? Paano yung itsura nun? Pahiga ba or patayo yung beam natin? So, yung longer direction niya, obviously, ito. Tapos, yung longer dimension daw na yan is parallel to the direction of the bending. Okay? So, kung magbe-bend tong beam natin, paano ba yung saang plane ba siya? Kumbaga, saang plane siya magbe-bend? Kung medyo nai-imagine niyo yung mga plane. Pag tinignan natin yan, ito kasi cross-section to eh. Pag tinignan natin siya sa elevation view, it will look something like this. Di ba? It will look something like that. Pag nag-bend yan, like this, dito siya nagbe-bend with respect dito sa plane na to, di ba? Can you imagine that? Kumbaga, dito siya naka-drawing sa papel na to, kumbaga. Okay? So ito yung ano niya, yung bending direction. Sabi niya yung longer dimension daw is parallel to this bending direction. So paano yung orientation ng beam mo? Pag ganyan, patayo, di ba? Kasi yung kumbaga yung papel, pag tinignan mo siya dito, parang nakatayo siya. Nakatayo siya. So parallel siya doon sa longer dimension ng rectangle. Okay? The cross section has a width B and a depth D. So ito daw, B daw to. Tapos ang total depth ay D. Where D is greater than B. So mas malaki daw yung depth kaysa sa B, sa width. Ang hinahanap lang sa tanong ay plastic modulus, yung Z. So hinahanap yung Z, tsaka yung shape factor na hindi ko alam kung paano basahin. Yan. Of the beam about its major axis. So about its major axis daw, which is this. So ano daw yung ano dyan, plastic modulus. Dyan sa portion na yan, kung saan nagaganap yung bending. Okay, so hinahanap natin yung Z dyan. Z tsaka yung, I don't know if this is eta eh. Tawagin na lang natin muna ng eta. Eta. I'm not familiar with the symbol eh. So how do we compute them? So first, we need to compute for the section modulus of the cross section. Okay? Kasi we can use the the fact that for the plastic moment to occur, dapat equal yung stresses acting on the compressive portion tsaka tensile portion ng cross section. Diba? Diyan natin makukuha yung ano eh, yung value ng Z. Diba? From there. Kasi diyan dependent yung ano eh, yung plastic neutral axis, 'di ba? So diyan natin makukuha yung ano, yung plastic modulus. Wherein dapat daw yung compression forces dito tsaka yung tension forces diyan equal. Okay? So with that, we can relate the plastic modulus and the section modulus. Especially kapag kukunin na natin yung ano, yung shift factor. So that's the first thing that we have to compute, yung section modulus nito. And section modulus is just equal to moment of inertia divided by c. So ano ba yung moment of inertia ng rectangle? It's just dh cube over 12. Ang nangyari lang dito, yung h natin, yung height, is equal to d. So palitan mo lang yung h ng d. So that's I. Tapos yung z natin, kakasabi ko lang kanina, that is just the distance from the neutral axis to the extreme fiber, either sa top or sa bottom. Okay? Pero since rectangle lang to, yung c top niya tsaka c bottom, parehas lang naman. Which is just equal to half of the depth, which is equal to d over 2. So divide mo lang yung dalawang yan, simplify, ito makukuha mo. So this is the section modulus of a rectangle, bd squared over 6. Okay, so since the cross-section is rectangular, its plastic neutral axis is still located at its elastic neutral axis, which is that the half depth of the section. The tension and compression forces form a couple, and the plastic moment can now be determined as equal to this. So yung dalawang to, yung compressive tsaka tensile forces na nararamdaman ng cross-section kasi nga nag-yield na siya, nakakabuo yan ng ng couple moment. Bakit ko nasabing nakakabuo siya ng couple moment? Kasi in the first place, parallel sila, tapos equal in magnitude pa sila. Di ba yun yung mga characteristic ng couple? Parallel and perpendicular. Sorry. Parallel and equal in magnitude, tapos opposite in direction pa sila. So, therefore, makakabuo sila ng couple moment. And from statics, we know that couple moment is just equal to the magnitude of one of the force times the perpendicular distance between them. Okay? So, from the figure a while ago, ito, burahin ko lang yung ibang nakasulat. From the figure a while ago, yung distance between the compressive force and the tensile force is what we call A. Okay? So, ngayon, kung ito ay kalahati ng depth, d over 2, d over 2. Tapos ito ay kalahati din ng depth, d over 2 rin. So, ano to? Saan equal yan in terms of d? Okay. So ito, since rectangle to, syempre yung location ng resultant niya, malamang nasa gitna. Nasa gitna ng d over 2. So kung gitna yan, malamang ito ay kalahati ng d over 2, which is equal to d over 4. Okay? And ganun din to. Yung sa ilalim, rectangle siya, so yung resultant niya, nasa gitna rin malamang. And ano ang gitna ng d over 2? Times mo lang sa 1/2, that is equal to d over 4. So therefore, if this is A, therefore A is just equal to d over 4 plus d over 4, which is just equal to d over 2. So, yan yung moment arm natin. Yan yung moment arm nitong C tsaka no T. Okay? So, yung moment na nagagawa niyan, yun nga yung tinatawag natin na plastic moment. Okay? So, therefore, yung plastic moment is just equal to C times d over 2, force times moment arm, kung C yung ginamit natin, or kung yung T, edi T times d over 2. Okay? So, yan yung nakikita nyo dito. Yan. So, parehas lang plastic moment yan. Kahit anong piliin niya. Okay? So, yung C, paano nga ulit kunin yung C or yung T? Yung C is just equal to area in compression times Fy. Yung T is just equal to area in tension times Fy. So, dito sa portion na to, yung upper portion malamang, yun yung area in compression. Okay, so what is that area? If we will be computing that area, what is the magnitude of that area? That is just a rectangle, and the area of a rectangle is just equal to B times half of the depth, which is D over 2. Okay, this is D over 2. Tawagin ko tong D over 2. Yan. So, B times D over 2 is equal to this. BD over 2. That is the area of the shaded portion here. Okay? Times Fy, ang makukuha natin ay yung compression. Yung sa tension, ganyan din naman yung formula. Okay? Times the moment arm, which is D over 2. And then, simplify mo na lang. Makukuha mo ay ito. This is the formula for finding the plastic moment. for a rectangular beam. Fy times b squared over 4. Okay, so how can we find the plastic modulus using that? How can we find the plastic modulus using that? Since we know that plastic moment is just equal to Fy times the plastic modulus, and since we already know what is the value of MP and we also know Fy, the only unknown here is the Z. Okay, so all we need to do is substitute the magnitude of MP, which is this, and Fy. Okay, so kung gagawin natin itong in terms of Z, it will be equal to this. Z is equal to MP over Fy. Substitute the magnitude of MP, which is this. Substitute mo yan dito. So it will be Fy times PD squared over 4. And then divided by Fy, cancel yung Fy. Matitira is BD squared. So therefore, the plastic modulus for a rectangular section is just equal to BD squared over 4. So since we already know that plastic modulus as well as the section modulus, we can already compute for the shape factor. And that is just the equal to the ratio of Z and S. So i-ratio mo lang yung Z, which is this, and then yung S, which is this. So maka-cancel yung B tsaka yung D squared. Ang matitira na lang ay 1/4 divided by 1/6. So therefore, the answer is equal to 1.5. So that is the shape factor for rectangular sections. Okay? Yan usually yung yung ratio ng section plastic modulus sa section modulus. Palaging 1.5. Okay? So ibig sabihin lang yan, yung section modulus is just 50% larger than the section modulus. Okay? So from this formula, Z over S is equal to 1.5. So therefore, Z is equal to 1.5 S. So therefore, Z is 50% larger than section modulus. Okay? So now, moving on to the next limit state that we don't want our beam to experience, which is the lateral torsional buckling. Structural steel beams can only reach its plastic state if it is properly braced laterally. However, another limit state may be reached by the beams, and this limit state depends on the adequacy of the lateral bracing provided on the beams. This limit state is called lateral torsional buckling. So this is what I am mentioning a while ago. So for the case of yielding, again, we can uh, we can just reach that point in the life of a steel beam if it will be uh, adequately braced laterally, meaning it will not have a tendency to deflect laterally, especially if it will be accompanied by a what we call torsional buckling. So just to have a imagination of the behavior of a steel beam experiencing lateral torsional buckling, we can look on this particular illustration here. So suppose we have a steel beam here. This is the side view or elevation view of the beam, and then say for example, it is resisting transverse load, which is this load, which is loaded in the plane of the web. So if you can just imagine what will happen to the beam if ever we apply a transverse load there. So it will be experiencing bending like this. The dotted or broken line that you are seeing here, it will be bending like this. Okay, so if ever you apply a transverse load to the beam, it will bend like this one. So this is what will happen to the beam if you will try to look at it on the side view. But if you will try to look at it on the top view, if ever it will experience lateral deflection, it will look something like this. So this is the original unstressed position of the beam, and then due to this applied load, the beam also experience bending on the other axis with respect to the minor axis. Okay, so meaning the beam did not just bend with respect to this direction, but also with respect to this direction laterally. Okay, so in a, in a, in addition to that, the beam also experience torsional buckling, which is this. So originally, this is the position of the beam, and then since it experienced torsional buckling, uh, or should I say, since it since it experienced torsional buckling like this, the section rotated from this current position to this particular position, to a deflected position. Actually, the main reason why the beam deflected laterally is simply because it experienced torsional buckling accompanied by lateral deflection. Okay, so usually this is the result if the load is applied at a certain eccentricity with respect to the longitudinal axis of the beam. Okay, so this is the scenario that we usually want to avoid, that are to be experienced by our steel beam. We don't want this scenario to experience by our steel beam. Therefore, we must provide adequate lateral bracing so that we can avoid this particular scenario. Since if we will be providing adequate lateral bracing, like for example, if you will have a bracing somewhere here, therefore this will prevent the steel beam from experiencing lateral torsional buckling, since it will not experience this scenario that you are seeing here. It will not tend to buckle laterally as well as experience torsional buckling. Okay, so for checking of lateral torsional buckling of beams, what we are usually concerned is the length of the unbraced length of the beam. We must provide lateral bracing in such a way that there will be adequate unbraced length with respect to the length of the beam. So we already defined what we mean when we say unbraced length. So unbraced length is just the length of the beam that is not braced. Okay, so like for example, if you will try to look here, there is a bracing provided by the hinge support here. Okay, but as you go here from this point to the other point, which is this, there is no longer a bracing. Okay, so therefore, from this point to this point, there is no bracing. Therefore, that is what we call the unbraced length. But if ever we will provide this particular bracing that we have here, we can see that from this point going to this point, there will be a bracing at this particular point. So therefore, from this point to this point, that is what we call the unbraced length. So we have minimized the magnitude of the unbraced length if whenever we provide additional lateral bracing. So the role of that lateral bracing is to prevent this scenario from happening, to prevent uh, the buckling of the cross-section laterally that will result to lateral torsional buckling, a combination of torsional buckling as well as lateral movement. Okay, so we don't want that to happen. Lateral torsional buckling occurs when there is lateral deflection or buckling accompanied by twisting or torsion due to the compression portion of the cross-section being restrained by the tension portion. Studies on the lateral torsional buckling of structural steel beams were done by Ure et al., De Vries, and Hetzman et al., and Galambos, among others. I don't know if I pronounced their names correctly. These studies show that structural steel beams do not necessarily reach its plastic moment strength depending on the distance between the lateral bracing supports. So yan na nga yung kanina ko pa binabanggit. We need to provide adequate lateral bracing so that the steel beam can reach the yielding state that we have discussed on the first portion of our lecture. Okay, so in order for the steel beam to reach this scenario wherein the whole section is experiencing yield stress, equal yield stress with respect to the compression and tension section or tension area of the steel section. We will reach this scenario if ever we will provide adequate lateral bracing. So that's very important, because if we will not provide adequate lateral bracing, the tendency is the beam will experience lateral torsional buckling, and it will prevent for this scenario to happen. So if you will try to look at this graph that I have here, the horizontal axis is actually the unbraced length, LB, and then the y-axis is the plastic moment. For the case of steel beam, the capacity is usually expressed in terms of the moment, specifically the plastic moment, because this is the we are assuming that this is the we are assuming that the plastic moment is the maximum moment that the steel beam can resist, because this is the ultimate load distribution that we have discussed a while ago. Okay? So wala nang lalagpas na ano dito na stress distribution. This is the ultimate na. Okay? So yan yung ultimate capacity ng beam natin that we consider yung MP. Okay? So dito sa y-axis natin, you can see here we have y-axis with respect to the moment capacity of the beam, and then the horizontal axis is with respect to the unbraced length. So again, the unbraced length is the length of the beam that is not braced. Okay. So according to the graph, if you will try to look at the graph, as you increase the magnitude of the unbraced length, the moment capacity of the steel beam decreases. Like for example, as you can see here on this particular point, the unbraced length is equal to this. And then, because of that, the corresponding moment capacity according to the graph is just equal to this, half of the plastic moment. Okay, but if the unbraced length is just equal to this, for example, we have a point here which is equivalent to an unbraced length equal to this, the corresponding plastic moment also increase. I mean, inversely increase. Okay, so obviously this portion here is larger than this magnitude. Okay, so that is what the graph means. As you increase the unbraced length, the moment capacity tends to decrease. The tendency is it will not reach this scenario that we are presenting here as you increase the distance from one brace to the other. Okay, that's why it's very important that you provide adequate spacing of lateral bracing as much as possible. If you can, as much as possible, provide lateral bracing as as near to each other as possible, although obviously that will be not economical always, aside from the fact that it will not be uh, uh, practical to do. Because if you can just imagine, if you will provide lateral bracing on this point, on this point, on this point, and on any other point, it will require uh, many lateral bracing, which is not economical and practical. Although sometimes, instead of putting individual lateral bracing, usually lateral bracing is provided by the slab that is being poured monolithically or compositely with the steel beam. So if you already seen a slab that is imposed on top of a steel beam, usually the lateral support or lateral bracing is already provided by the slab. And the good news there is lateral bracing is provided all throughout the length of the beam for this particular case. Okay, instead of putting individual bracing using another beam like this, instead of putting lateral bracing using another beam like this, you can instead put lateral bracing using a slab. And the good thing there is that the lateral bracing is actually provided all throughout the length of the beam. Unlike here, the lateral bracing is just provided at some point, at some specific point from the length of the beam. Okay, The effects of lateral torsional buckling on structural steel beams may be reduced by providing adequate lateral bracing supports. These supports may be continuous lateral support by embedment of the compression flange in a concrete floor slab, or lateral support at intervals provided by either cross beams, cross frames, ties, or struts. So yan na nga yung binabanggit ko kanina. The lateral support can be provided by slab continuously. If you have provided a slab as a lateral support, it will be continuously supported all throughout its length. So the scenario can be look like this. So as you can see here, the steel beam is the compression flange of the steel beam is actually embedded inside the concrete slab. So with that, you already provided lateral bracing on the top flange all throughout the length of the beam. Because if you will try to imagine what will the beam will look like on the side view or the elevation view, it will look something like this. If you will just try to imagine. Okay, so this is the top slab. This is the top slab. The top flange is actually embedded inside it. So this is the top flange, and then this is the bottom flange, and this is the web. Okay, so you can see here at the top flange, lateral support is provided by the slab all throughout the length of the beam. Okay, so you can do that configuration, or you can also do this if you don't want the steel beam to be embedded inside the concrete slab. You can just put the slab above the steel beam and then just put shear connectors, which are this. These are connectors. So those shear connectors are those things that actually connect the steel beam to the concrete slab so that they can act as one. Okay, so horizontal shear stresses is usually transferred from the slab to the steel beam using those shear connectors. Okay, so those are just two of the examples of how to provide continuous support to the beam, so that lateral bracing will be provided all throughout the length of the beam. Although you can also provide any of these options to provide lateral bracing to the steel beam. Although these configurations that you are seeing here usually is provided at a certain distance from each other. Okay, you can either provide another beam to act as a lateral support to the steel beam that we have here, or you can provide this open web joists or angles or channel strut with stiffener, or roof purlin. Although each of these are just lateral bracings provided at a certain point along the length of the beam. So meaning, if this is the I-beam, if this is the elevation view of the I-beam, if that is the top flange, and this is the web, and this is the bottom flange, usually these bracings are just provided at a certain point along the length of the beam. Like for example, this beam can just be provided here, and then here, and then here, and then here. So you still have what we call the unbraced length. Okay, so that is the unbraced length, LB. Okay, so we want that LB to be minimum as possible. Okay, so if the lateral bracing, or should I say, if the unbraced length is as small as possible, therefore you can expect that your steel beam will avoid lateral torsional buckling. Much there is a much less, or should I say, there is a lesser chance that your steel beam will experience lateral torsional buckling if you will provide lateral bracing as near to each other as possible. Okay, for the case of individual or separate lateral bracing, although this type of lateral bracing is much preferred, although this type of lateral bracing is usually used for composite construction. When you say composite construction, you are using two different material, the concrete and the steel. For the case of non-composite construction, meaning you are just using one or single type of material, which is steel, it is preferred to do this. Okay. You are using a steel to provide lateral bracing to another steel. Okay, in this case, you are using concrete to provide lateral bracing to a steel material. Okay, so usually you can see this on composite construction. Okay, so those are just the different ways to provide lateral bracing to a steel beam so that lateral torsional buckling can be avoided. So if you want to have more information about lateral torsional buckling and its influence on the strength of beams, you can watch this video here. Although we will not we will no longer watch this video because it is worth 1.5 hours. So that is very long period of time. So we'll just skip that. So just watch this video whenever you have time. Okay. So we will just move on to this. So just for you to have a visualization on how lateral torsional buckling is happen, just for you to have a visualization on how lateral torsional buckling happens. Let us just watch this very short video about beam global buckling. Buckling happens when a member in compression becomes unstable because of its slenderness and load. Beams experience lateral torsional buckling or LTB due to buckling of the compression flange of a beam. So sometimes we usually use the term LTB or the acronym LTB to indicate lateral torsional bucklings because obviously the word the term lateral torsional buckling uh, is very long. Okay, so usually we use the acronym LTB. So you can see here, our beam is composed of compression flange and a tension flange. The red one is the compression flange, which experiences compression, obviously, while the tension flange obviously experiences tensile stresses. A compression flange by itself would tend to buckle much like a column. Paano magbuckle yung column or compression member, ganun magbabakal yung top flange natin or yung compression flange, like that. Okay, for the case of flexural or for the case of beams, whenever a beam, a, an I-beam experiences bending, that the compression flange most likely manifests the behavior of a compression member. Obviously, because it experiences compression. The web, however, prevents the flange from buckling about its minor axis. So that's the purpose of the web. It prevents the buckling of the element with respect to the minor axis. But if there is enough compression with no lateral support, the flange and web will buckle together. So that's the importance of lateral bracing or lateral support to prevent lateral buckling. Just like that. That is what we call the lateral buckling. The tension flange, which is stable, restrains the compression flange and web, causing the beam to twist. The result is lateral torsional buckling or LTB. So pag pinagsama-sama na natin lahat ng element, uh, ganito na yung magiging behavior niya. It will prevent the bottom flange, the tension flange will prevent the beam from experiencing lateral buckling, resulting to lateral torsional buckling. There. That's what we call the lateral torsional buckling. So the beam experiences lateral deflection as well as torsional buckling. Umiikot din. Nagmo-move na, nagde-deflect na siya, tapos umiikot pa yung cross-section niya. We calculate LTV based on a graph with three regions, each representing a different mode of resistance. So this graph is similar to the graph that I have shown a while ago. The x-axis is composed of the unbraced length, LB, and then the y-axis is composed of the moment capacity of the beam. So you can see here as you increase the magnitude of the unbraced length habang layo-layo yung yung mga location ng mga bracing, the moment capacity of the beam tends to be much lesser. Okay? Pero kung medyo maliit yung yung spacing between one bracing to another, mas lumalaki yung capacity ng beam natin. Okay? Magkakaroon pa siya ng chance na umabot doon sa maximum moment capacity niya that we assume theoretically, which is equal to the plastic moment. Oops. Ulit. Stocky or continually laterally braced beams will not experience LTB. They can carry their full plastic moment or MP. So you can see here, kung medyo maliit yung spacing between one bracing to the other, mas nakagkakaroon siya ng chance to attain its maximum possible capacity, which is equal to the plastic moment. Okay? Up to that certain magnitude of lateral bracing. I mean, up to that certain magnitude of unbraced length, LB. Hanggang diyan sa magnitude ng LB na yan, kunyari yung spacing between one bracing to the other, less than or equal to LB, there is a high chance na ma-attain niya yung maximum capacity niya, which is equal to the moment, the plastic moment. Okay? Pero makikita mo dyan, pag lumagpas na dun sa certain magnitude of spacing of the bracing, yung yung spacing ng mga bracing natin, you can see, nagkakaroon ng trend na nagdi-decrease. Nagdi-decrease na yung yung moment capacity ng beam natin habang lumalaki pa yung spacing between one bracing, one lateral bracing to the other. So, ibig sabihin lang nun, merong kumbaga uh, efficient magnitude of lateral bracings. I mean, there is an efficient unbraced length that will ensure that the beam will still uh, uh, experience the maximum capacity that it can offer, which is just equal to LP. That's why you can see later on that we usually include that magnitude of unbraced length LP to the computation of the capacity of a beam with respect to lateral torsional buckling or LT. Slender beams with a long unbraced length experience elastic lateral torsional buckling. So you can see here, so obviously habang lumalaki yung spacing between one lateral bracing to the other, obviously medyo humihina yung natin, yung beam natin, lumiliit yung niya yung corresponding moment capacity niya. Pero merong point diyan, yung merong certain magnitude of spacing wherein the beam will still experience elastic lateral torsional buckling. Ibig sabihin, mag-buckle man siya, mag-experience man siya ng lateral torsional buckling, once na tinanggal mo yung load, babalik pa rin siya sa original form niya. And that magnitude of spacing of the lateral bracing is what we call LR. Okay, kumbaga yan yung efficient spacing ng mga lateral bracing to ensure elastic lateral torsional buckling. Elastic lateral torsional buckling occurs when the member is slender enough to deflect without yielding. So usually nagaganap yung elastic lateral torsional buckling sa mga slender member. Ibig sabihin sa mga member na mahaba yung distance from one bracing to the other. Okay? So if you just want to imagine how LTB is being experienced by a beam, you can see here we have a beam originally upright, and then we have applied uniform load, and then this is what happened. Nagkaroon ng lateral deflection as well as torsional buckling. Okay? So, yan yung iba't ibang view yan. Makita mo, umusog yung midspan tapos nag-deflect. Nag-deflect yung midspan tapos nag-rotate pa yung section niya. So, ibig sabihin, lateral torsional buckling yung naganap. So, yan. Yan yung itsura ng beam sa iba't ibang view. This type of buckling is elastic. When the load is removed, the member returns to its original shape. So, that's obviously the definition of elastic. So, ibig sabihin, pag tinanggal mo yung load, dapat babalik pa siya sa original form niya, sa upright position. So, yan. So, makikita mo, bumalik pa siya sa upright position niya. Ibig sabihin, yung buckling na naganap is actually elastic buckling, elastic LTB, elastic lateral torsional buckling. And again, nagaganap lang yun usually kapag medyo medyo slender. Medyo slender enough yung beam mo so that uh, it can still deflect elastically. Kumbaga hindi siya masyadong lalaban. Okay? Kasi pag masyadong stiff yung beam mo, kumbaga hindi siya masyadong slender, masyado siyang stiff, lalaban yan to the point na magkakaroon siya ng sobra-sobrang stress na mararamdaman. To the point na lalagpas na siya dun sa yield stress. So, magkakaroon na ng yielding. Okay? So, that's the advantage kapag medyo slender yung member mo. Although, syempre, yung corresponding advantage na yun, syempre, may corresponding disadvantage kapag slender. Shorter beams that are not laterally supported may experience inelastic lateral buckling, lateral torsional buckling. So, yung mga beam na may spacing ng mga bracing between LP and LR, nakaka-experience naman yun ng inelastic lateral torsional buckling. So, obvious naman yung difference between them. So, pag tinanggal mo yung load, hindi na siya babalik sa sa original form niya. Hindi na siya magiging upright. Meron ng permanent deformation. Inelastic lateral torsional buckling is similar to elastic lateral torsional buckling, but the shorter unbraced length allows for a larger capacity and does not allow enough deflection to prevent the residual stresses in the steel from causing it to yield as it buckles. So yun na nga, since masyadong stiff na yung beam mo, since masyadong maliit yung spacing between lateral bracings, mas lumalaban siya sa stresses na ini-induce ng mga applied load. Ang tendency, ang result, na mas nakaka-experience siya ng mas malaking stress. Kasi nga lumalaban siya. So, mas na-stress siya. So, since mas na-stress siya, mas malaki yung stress na nararamdaman niya, lumalagpas na dun sa yield stress. Okay? Since lumagpas siya dun sa yield stress, alam naman natin ang result pag lumagpas ka na sa yield stress, sa yield point, magkakaroon ng permanent deformation, hindi ka nababalik sa original form kahit tanggalin yung applied load. Okay? This type of buckling is inelastic. The non-elastic portion of the deformation remains when the load is removed. So, yun na nga yung binabanggit ko. Magkakaroon ng permanent deformation. Kahit tanggalin yung load, ayun, medyo nagkaroon na ng permanent deformation. Yan, nag-buckle na siya laterally, permanently. Okay, so yan yung iba't ibang view nung nag-buckle siya. Note, providing bracing regularly along the length of the beam will keep the compression flange stable and prevent LTB. So, yan na nga yung binabanggit ko kanina. Baga meron lang most efficient distance from one bracing to the other, which is equal nga hanggang sa LP. So, kung para gusto mo mapigilan yung lateral torsional buckling ng beam, might as well just ensure na yung spacing ng bracing mo ay from 0 to LP. Kung ano man yung magnitude ng LP na usually kino-compute natin yan. Okay? So kung yung spacing ng mga bracing mo ay hindi lalagpas sa LP, you can ensure na it will prevent lateral torsional buckling. So hindi magaganap tong dalawang to. Hindi magaganap yung inelastic LTB tsaka yung elastic LTB. Talagang magbe-bend lang siya. Okay, hindi siya magbe-bend on the minor axis but on the major axis lang, resulting to uh, uh, experiencing the maximum moment capacity that it can offer, which is equal to the MP, the plastic moment. Okay? So, yan yung mga check natin sa code. Later on, pag nakita nyo sa code provisions, yan yung check natin. yung LP na yan with respect sa lateral torsional buckling. So in order for us to ensure that lateral torsional buckling uh, will not occur on our beam, we usually make sure na yung bracing niya within the limits of LP. Okay? Note, local buckling is still a limit state that must be considered in addition to global buckling. So bukod dyan sa global buckling na yan na nagaganap sa mga steel beam, of course, we also need to check local buckling which will be discussed later on. Okay, so ito na nga yung binabanggit natin, yung about sa local buckling. So ito na yung pangatlong limit state na check natin whenever we design steel beams. So recap lang, ano yung mga limit state na check natin. Ayaw nating maramdaman na or ma-experience ng beam natin. Una, ayaw natin siya mag-yield. Yung yielding, that's why check natin siya sa yielding. Okay? Pero yung yielding na yan, ma-attain mo lang if there is enough or adequate lateral bracing. Pag hindi enough yung lateral bracing mo, the tendency is maka-experience yung beam mo ng LTB, lateral torsional buckling. Pero aside from these limit states, there is still a tendency na magkaroon ng tinatawag natin na local buckling yung beam section mo. Ibig sabihin, nagkaroon ng buckling pero hindi yung buong length ng beam yung nagbuckle. Ang nagbuckle lang is yung particular point lang sa length ng beam. At yung mismong nagbuckle ay yung mga section components lang, whether flanges or yung web yung nagbuckle. Okay, as previously discussed in the previous module, Module 3, compression members, local buckling occurs when the section components of a member, such as flanges and webs, becomes unstable due to applied loads. This occurs due to slenderness of these components. The susceptibility of these components to be unstable is measured by its own slenderness measure, known as the width thickness ratio or lambda. The width thickness ratio of a flange is denoted as lambda F, while for a web, it is lambda W. So this topic is actually somehow similar to the topic of local buckling with respect to the compression member that we have discussed from the previous module. So again, the slenderness or the susceptibility of a section component to buckling is also measured using width thickness ratio or the slenderness ratio. Although for the case of local buckling, we usually call the slenderness ratio as the width thickness ratio, or simply the ratio of the width to the thickness. Although we have somehow different definition of width pagdating dito sa local buckling. So later on, makikita nyo yung ibang definition ng width. So it's not literally na width nung kunyari nung flange. Hindi siya literal na width ng flange. Sometimes the width that we usually check is actually half of the width of the flange. Okay? But overall, what they are called width thickness ratio lambda. Lambda F kapag width thickness ratio ng flange, lambda W kapag width thickness ratio ng web. Structural steel section components subjected to flexure are classified into three in terms of their local stability as follows. Meron din tayong compact tsaka non-compact tsaka slender dito sa compression sa flexural members. Okay, just like sa compression members. So recap lang ano ibig sabihin ng compact. These are section components that are not susceptible to local buckling. Not susceptible. Ibig sabihin, medyo maliit yung chance, kung hindi man zero, yung chance to experience local buckling. Yung kabaligtaran niyan is yung section components, yung slender, which are section components that are highly susceptible naman to local buckling. Okay? Compact, hindi siya susceptible to local buckling. Slender, susceptible, highly susceptible to local buckling. Yung in between them, na medyo wala yata to sa compression member. I think sa compression member, compact lang tsaka slender. Pero dito sa flexural member, meron pa tayong tinatawag na non-compact. Okay? So yung non-compact is the intermediate classification between compact and slender. So yung non-compact are section components that are slightly susceptible to local buckling. So meron pa ring tendency to buckle pero medyo maliit na lang compare mo naman sa mga slender section components na highly susceptible to local buckling. Okay, compact sections are structural steel sections which have all of its components classified as compact. Non-compact sections are structural steel sections which have at least one component classified as non-compact, but the rest are compact. Slender sections are structural steel sections which have at least one component classified as slender, but the rest are either compact or non-compact. Most hot-rolled eye-shaped sections are considered to be compact. However, for this course, local stability checks will always be performed. So just like sa compression members, guys, meron din tayong mga tinatawag na compact sections dito sa 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 flexural members. Yung definition ng compact, non-compact, at slender sections are the following. So take note, um, meron tayong tinatawag na compact section component tsaka compact section. So when you say compact section component, ibig sabihin component lang yung pinag-uusapan natin doon. Whether flange or web or another flange, bottom flange. Okay? So yung isang-isang yan, tigi-tigisang yan, if we will try to classify them individually, we can call them compact section, compact section component or non-compact section component or slender section component. Because these three here are just components of the whole section. Pero kung i-classify natin yung buong section as one, we can also call them compact section, non-compact section, or slender section. Okay? So, paano natin masasabi na yung section, yung buong section ay compact? So, we can say that the section is compact if all of its components are classified as compact. Ibig sabihin, compact yung flange or flanges, pati yung web. Okay? Pag non-compact naman, dapat at least one component is classified as non-compact and then the rest are compact. So, medyo lagay ko lang dito. Lagyan lang natin ng konting definition. Pag compact, all are compact. Yung mga section components ha. Pag non-compact, dapat at least one non-compact. Tapos, the rest, yung dalawa, compact dapat. Okay, according to this definition. Pag slender section naman, at least one is classified as slender. So, meron kang slender na isang component and then the rest either compact or non-compact. Okay? So, yan yung mga classification ng mga local stability ng ng mga sections natin. So, may mga sections na compact, may mga sections na non-compact, may mga sections na slender. Okay? Pero most hot-rolled eye shape naman yung mga eye, mga katulad nito. Most of them naman considered as compact. Ibig sabihin, usually yung dalawang flange niyan tsaka yung web, compact pare-pareho. So therefore, yung buong section ay compact. So that's the usual scenario. Although, kahit na alam natin na compact na siya, for this particular course, we will still practice checking local stability for the sake of practice. Okay? Kahit alam natin dapat na siya, compact na by definition. Pero check pa rin natin. Check pa rin natin yung local stability niya. Okay? Kasi malay mo, baka nung chinek natin yung isang I-beam, biglang slender pala siya due to the dimensions. Diba? Pero yun nga, most of them, compact naman. Local stability checks for structural steel sections may be done by checking the requirements of Section 502.4 of 2015 NSCP Volume 1. In case of hot-rolled eye-shape subjected to flexure, tables 502.4.1 and 502.4.2 of the 2015 NSCP Volume 1 may be used. For flanges, case 1 should be used. For webs, case 9 should be used. Components are classified as compact if lambda is less than lambda r. Components are non-compact if lambda p less than or equal to lambda less than to lambda r. Otherwise, it is slender. Calculation of lambda for flanges and webs may be seen on tables 502.4.1 and 502.4.2 of NSCP 2015 Volume 1. So, this is how we can classify every section components, whether they are compact or non-compact or slender. So we have to compare them with respect to this two maximum or maximum width thickness ratio. Ito yung mga kumbaga limitation ng mga classification. Okay? Kapag yung lambda daw na na-compute mo ay less than sa lambda p, I think this must be lambda p. Nagkaroon lang yata ng typo error. Lambda p yata yan. Kapag yung na-compute mo na lambda is less than sa lambda p, therefore it can be classified as compact. Okay? Kapag nasa pagitan naman ng lambda p tsaka ng lambda r, sabihin in between them, you can consider them as non-compact. Okay? Otherwise, kung medyo greater than lambda r na, we can consider them as slender. Okay? So yung mga formulas to compute for the corresponding formula for different section components can be found on NSCP 502.4. Okay, sa section 502.4, specifically sa table 502.4.1 tsaka sa 502.4.2. Okay, although since dito sa course natin, we are just limited to studying I sections, puro I section lang tayo, although meron pang ibang mga section, yung C section or channel, or mga angle, or mga T, WT, and etc. etc. Meron pang mga ganyan, pero we are just focusing on I beams or I sections. That's why just to give uh, just to relieve you from the stress of searching what particular case will be applicable for the specific section that we have here, we already extracted the particular case that will be used for checking the local stability of I sections or the section components of an I beam or I section. So similar to the compression member, if you will try to look on table 502.4.1 and point 2, you can see there a table like this, and then meron siyang mga column dyan. Nandito yung column for lambda p, the formula for lambda p, and then formula for lambda r, and then nandito yung particular element, whether ano ba siya, I section ba siya, C section, or channel section, angle section, etc. etc. Okay, so iba't ibang element, iba't iba yung lambda p and lambda r, iba-iba yung mga limitation nila. Okay, so may mga case yan. Case 1, this. Case 2, this, and so on and so forth. So since, again, limited lang tayo sa I-beam, sa I-sections, ang kailangan lang natin dun sa maraming cases na yon ay yung case 1 for checking of the local stability of flanges, and case 9 for the local stability of webs. Okay, so we already extracted those formula related to case 1 and case 9. Case 9, which are for flanges and webs, which are this. Okay, so if you will just try to refer to the code, makikita mo rin itong similar formulas na to na nakalagay sa case 1. This is for case 1. Ayun lang, I'll just remove some of the inks. So this is the case 1 for flanges, and then this is case 9 for web. Okay, so you will just see similar formulas dun sa code. Okay, ito yung mga limitation nila. Kapag ang lambda mo na na-compute using this formula ay less than sa lambda p, therefore it's considered as compact. Kapag yung lambda mo nasa pagitan ng lambda p tsaka lambda r, less than or equal to, you can consider it as non-compact. Kapag naman yung lambda na na-compute mo ay greater than na sa lambda r, it's already considered greater than or equal. It's already considered as slender. So just like sa compression members, iba't ibang section provisions yung ginagamit natin for compact, for non-compact, tsaka sa slender. For compact, yung section or from the code that we usually use is section 502.4. If ever yung nakuha yung section is slender, you have to refer to other sections ng code to be able to compute for its capacity. Okay? So for this particular case, guys, take note, we are just limiting the discussion to compact sections. Okay, so that's why we can just refer to section 502.4. But again, if ever, you have to look to other sections of the code. If ever non-compact or slender yung nakuha nyo na section. Okay? So just to practice the checking of local stability, let us answer this sample problem that we have at hand. So this is for local stability check of a double section considering flexure. So the question asks for check the compactness of the W14 by 82 hot rolled ASTM 36 section under flexure. Okay, so you can see here it was mentioned that the material is composed of ASTM 30 A36. So again, as of this moment, I hope you already know what is the yield strength of ASTM A36. So you have to memorize it. ASTM A36 has a yield strength Fy equal to 36 KSI or equal to 36,000 PSI, or if you will try to convert it to SI, that is just equal to 248 supposedly, but approximately equal to 250 megapascal. Okay, so even if it is not given on the problem, supposedly you already memorized that. Although you can also check on that on the code, you can see that on steel construction manual, AISC steel construction manual, it is written there, or you can check that on the ASEP handbook if it is written there. I'm not so sure if it is written there, but I'm sure that it is written on the AISC steel construction manual. So just try to browse the steel construction manual to see that particular table that mentions the different yield strength as well as the ultimate strength of different steel materials. Okay, so we are just being asked to check the local stability of W14 by 82. So this is W14 by 82. So these are the corresponding properties of a W14 by 82. But take note, these are just geometric properties. Okay. So the section type is W, its unit weight is 1.19 kilonewton per meter or 82 pound per feet. So again, I suppose you already know what is the meaning of the name of a wide flange. The first digit or the first number here corresponds to the total depth of the wide flange. So it means the total depth here is equal to 14 inches or 363.22. So multiply that to 25, uh, you can get the total depth in terms of mm. Okay, and then the next number here is the weight per length. So in this case, it is usually in terms of pound per feet. Although you can verify this on the code on the AISC steel construction manual as well as on the ASEP handbook, because usually the units or the dimensions here are usually given on the header of every column on the table. Okay, so you can verify that. So the 82 pound per feet, if you will try to convert it to kilonewton per meter, suppose it is equal to 1.19 kilonewton per meter. Okay, but again, you can verify that on the steel construction manual if ever I was wrong here. Okay, so the total height or the total depth is equal to 363. The flange width 256, web thickness 12.95, the thickness of the flange 21.72. And again, these dimensions, these geometrical properties that you are seeing here, just came from CSI Steel. So this is just a mobile app that you can use for quick reference for the different geometrical properties of different steel sections. Okay. Although again, take note, there are usually differences between this information that you have here and the steel handbook, ASEP steel handbook. There will be differences, especially on the values as well as the notation. So for our course, always refer to ASEP steel handbook. So we just refer to this CSI steel app simply because for easiness of the solution. I mean easiness of the writing the solution. Okay. So that's why dito tayo nag-refer sa CSI state. But sa mga test natin, always refer to as if still handbook. Okay? So how do we check the local stability of AW14 by 82? Obviously, if you want to check the stability of the whole cross-section, we need to check the local stability of each individual section components, which are the top flange, the bottom flange, and the web. So we need to check the individual local stability of the section components. Although in this particular scenario or for particular problem, since the top flange and the bottom flange are just identical with each other, therefore, we just need to check one flange and then one web. We just need to check the local stability of one flange and one web. We no longer need to check the other flange simply because it is identical to the top flange. Okay, so how do we check for the local stability of a flange? You can refer to the code, use the case 1 for flanges. Okay, so for that, we just need to find out the width thickness ratio. Width thickness ratio B over T. Okay, we just need to find B over T, which is equal to lambda, the width thickness ratio. That because that is the measurement of how slender a section component is. And then we just need to compare that ratio to the limits appropriate for the section component, which can be found on the code. Okay, although you have to realize that the width thickness ratio is not always the literal width over thickness ratio. Just like for the case of flange compactness, the width that is being defined on the code is not actually the total width of the flange. It's not this, but half of that. Okay, so this is the width that is being mentioned on the code. You can see that on the code. If you will try to if you will try to read the code, you can see there that there is a note that the width for a flange is equal to half of the width of the flange, not the whole width itself. Okay, so you can see here the B is not actually the width, but half of the width of the flange. The thickness is the same. The thickness is the same. It's just the thickness of the flange. So you can see here the BF or the width of the flange is equal to 256. That's why it's written here 256. Divide it by 2 and then divide to the thickness of the flange, which is equal to 21.72. The ratio will be equal to this. So that is lambda. That is the width thickness ratio of this particular flange of W14 by 82. And then after computing that, all we need to do is compare that to lambda p. That's why we need to compute for lambda p. And the formula for lambda p is equal to 0.38 square root of E over Fy. The E of a steel is 200,000 megapascal. Fy is given, although even if it's not given, you have to know it already. You have to memorize it. That is equal to 250 megapascal. The result is equal to this. Okay, comparing the two, we can see that lambda, the width thickness ratio, is less than lambda b, the limit for compactness. Okay, lambda p is actually the limit for compactness. As long as the width thickness ratio is not exceeding the lambda p value, we can still say that it is compact, and that is the case here. Okay, since lambda is less than to lambda p, therefore we can already say that the section flange is compact. Okay, we no longer need to check lambda r. Okay, why? Because simply because we already found out that the lambda is less than lambda p. Therefore, we already found out that the section is compact. Okay, since simply because we know that if the lambda is less than lambda p, therefore we can already say that it is compact. Okay, if ever the lambda that we have computed is larger than lambda p, that's the time that we have to compute also for lambda r. Simply because lambda might be in between lambda p and lambda r or greater than lambda r. Okay, that's the time that you will need to check for lambda r. If ever the width thickness ratio that you have computed is larger than lambda p. Okay? Kasi kapag larger than lambda p siya, you're not sure if in between ba siya ng lambda r or larger ba siya ng lambda r. Kasi kung in between siya ng lambda p tsaka lambda r, we can say that it is not non-compact. Okay? According to the formula that I have given a while ago. But kung lag pa siya sa lambda r, slender na siya. So, if ever, iba na yung mga provisions ng code na gagamitin mo for those cases. But again, for the particular case at hand, we already found out that the section is compact. Therefore, we can say that the section flange is compact or are compact since we have two flanges. Okay, but that is not enough to say that the whole section is compact. We have to check as well the compactness of the web. And again, for the formula for the compactness of the web is again simply width over thickness ratio. Okay, so we just have to find the width of the web. So take note, the width of the web is just this. It's not the distance from the bottom flange to the top flange. Okay, this is the width of the web that we are talking about. So you have to compute for that. Okay, so how do you compute for the width of the depth, the width of the web? All you need to do is subtract twice of the flange thickness to the total depth, which is what is written here, and then divide it by the thickness. Since we are computing for width thickness ratio. Okay, the thickness of the web is given here. It's 12.95. Substitute and then compute. You can find the width thickness ratio of the web of this particular section W14 by 82, and then compare that to lambda p to know if it is compact or not. So this is the formula for lambda p for the web. That's actually case 9 for the web. Okay, if you will try to look on the table that is written on the code, that is actually case 9. This is the formula for web compactness. So substitute the corresponding values, you can compute for this 106. Compare the two, so you can easily see that the limiting value for compactness, or should I say, the limiting value for compact classification is actually larger than the actual width thickness ratio of the web. Therefore, we can easily say that the section web is compact. Okay? We no longer need to compute for lambda r simply because hindi naman lumagpas yung width thickness ratio sa lambda p. Kung lumagpas yan sa lambda p, yung width thickness ratio, it's either in between siya nito or larger pa siya nito. Yan. Hindi, baliktad. Yan. Okay. So since hindi naman lumagpas, you no longer need to compute for lambda r. Kasi you already have a classification which is compact na. So since compact yung dalawang flange and compact din yung web, therefore all of the section components are compact. Therefore, we can say that the whole section, the whole W14 by 82 is a compact section. So therefore, since compact section siya, we can refer to the provisions of section 504.2, if I'm not mistaken. It's 504.2 of the NSCP 2015 Volume 1 Code. Okay? 502 pala, sorry. It must be 502.4 according to this portion here. So since compact section siya, nakita natin yung W14 by 82 ay compact section, we can refer to section 502.4 of NSCP 2015 Volume 1 for the different provisions related to the computation of the capacity of a compact section. Okay? If ever you found out that the section is non-compact or slender, you need to refer to other provisions of the code. Okay? So that's the purpose of checking the local stability of the section.